The letter that shook NASA. A Harvard astrophysicist walks into Joe Rogan's studio and accuses NASA of hiding evidence. 4 weeks of silence. Images that could change everything, locked behind government walls. Then a congresswoman does something unprecedented. She puts it in writing. 6 demands, 1 agency. What happened when 3I-ATLAS disappeared behind the sun on October 29th? NASA knows. They're just not telling you. If you're finding value in this deep dive, hit that like button and subscribe so you don't miss what's coming next. And tell me in the comments where you're listening from, what time it is there, and whether you think NASA is deliberately withholding this data or if it's just bureaucratic delays. October 31st, 2025. While most of America prepared for Halloween, Representative Anna Paulina Luna from Florida's 13th District signed her name to a document that would send shockwaves through NASA headquarters. The letter, addressed to Acting Administrator Sean Duffy, contained 6 specific requests. Not suggestions, not polite inquiries, demands backed by congressional authority. At the top of that list sat something that had been quietly troubling the scientific community for nearly 4 weeks. High-resolution images of 3I-ATLAS, captured by the HiRISE camera aboard the Mars Reconnaissance Orbiter on October 2nd and 3rd, images that should have been released to the public within days, images that by late October still hadn't seen the light of day. Think about that for a moment. We live in an era where NASA streams live video from Mars rovers, where Hubble images hit the internet within hours, where transparency in space science is supposed to be the default. And yet here was a congressman formally requesting data that taxpayers funded, data that by every standard protocol should already be public, data about an object that happens to be only the 3rd confirmed interstellar visitor in human history. The timing of Luna's letter carries weight that goes beyond simple bureaucratic frustration. Just 3 days earlier, on October 28th, Harvard astrophysicist Avi Loeb sat across from Joe Rogan in what would become one of the most explosive podcast episodes of the year. For 2 hours and 15 minutes, Loeb laid out a case that left Rogan visibly stunned. NASA, Loeb claimed, had not only failed to release the HiRISE images, but had actively stonewalled his personal requests for the data. I wrote to the principal investigator of HiRISE, Loeb told Rogan, asking, "Can I get the data? I'm a scientist." The response? Silence. Nothing. 4 weeks of institutional void. But here's where the story takes on a different character. This wasn't some fringe researcher making wild accusations on a conspiracy podcast. This was Avi Loeb, former chair of Harvard's astronomy department, founding director of the Black Hole Initiative, a man who served on the President's Council of Advisors on science and technology. When someone with that pedigree goes on the world's largest podcast and accuses NASA of withholding evidence, people listen, and apparently so did Congresswoman Luna. The connection between the podcast and the letter isn't speculation. Loeb himself confirmed it in a Medium post published the same day Luna's letter went public. Joe Rogan suggested that I contact the interim NASA administrator Sean Duffy, Loeb wrote. The following day, I corresponded with Congresswoman Anna Paulina Luna regarding a related formal request from NASA. Following our exchange, Representative Luna wrote a brilliant letter to NASA's acting administrator Duffy. That timeline matters. Rogan podcast on October 28th. Luna correspondence begins October 29th. Official congressional letter dated October 31st. 72 hours from podcast to congressional intervention. That's not how government usually works. So what exactly did Luna request? The letter outlines 6 specific categories of data, each one carefully chosen to address a particular gap in the public record. First and most prominently, those HiRISE images from October 2nd and 3rd. Luna's letter specifies exactly why these matter. When 3I-ATLAS passed within 30 million kilometres of Mars, the HiRISE camera could achieve a spatial resolution of approximately 30 kilometres per pixel. To put that in perspective, that's about 3 times better than the best image we have from Hubble, taken back on July 21st. But there's another crucial difference. The Hubble image showed 3I-ATLAS from an edge-on perspective, Earth and the Sun separated by only about 10 degrees relative to the distant object. The HiRISE image offers a sideways view, perfect for understanding the geometry of mass loss and the mysterious glow that surrounds this thing as it approached the Sun. The second request targets something equally important, but less visible to the casual observer. Luna asks NASA to release any supplementary data from the Mars Reconnaissance Orbiter, the Perseverance rover, or other Mars assets that may have detected unusual activity near Mars around or after October 3rd, when 3I-ATLAS passed within approximately 30 million kilometres of the planet. This language is deliberate. Unusual activity. Not just expected cometary behaviour, not just standard outgassing or brightness changes, but anything that doesn't fit the normal pattern. What could that mean? The letter doesn't specify, but the implication hangs in the air like a question mark. Request 3 broadens the scope even further. Luna asks for any data on 3I-ATLAS obtained by other missions, including the Parker Solar Probe or active observatories under NASA's purview. This matters because 3I-ATLAS spent most of late October hidden behind the Sun from Earth's perspective, but spacecraft positioned elsewhere in the solar system could potentially observe it during that critical perihelion passage. If Parker Solar Probe caught anything, if any of NASA's solar observation satellites tracked it during those crucial days when ground-based telescopes were blind, the public deserves to know. The 4th request ventures into more speculative territory, but it's grounded in solid mission planning. Luna encourages NASA to fund additional observations of 3I-ATLAS by the Juno mission near Jupiter, utilizing all available instruments including radio sensors. This isn't a new idea. Loeb and his collaborators, Adam Hibbard and Adam Krul, published a paper proposing exactly this, calculating that if Juno had its initial fuel supply, it could potentially intercept 3I-ATLAS when the object makes its closest approach to Jupiter on March 16th, 2026. Even with limited fuel, a mild engine burn could bring Juno significantly closer to 3I-ATLAS's path. Luna's letter explicitly backs this proposal, even suggesting a mission extension at a cost of about $15 million per 6 months. For context, that's pocket change in NASA's budget, especially for a chance to study an interstellar object up close. Request 5 takes aim at the historical record. Luna asks NASA to release all data on confirmed or candidate interstellar meteors contained in the Center for Near-Earth Object Studies database, maintained by the Jet Propulsion Laboratory. She specifically mentions the interstellar meteor detected on January 8, 2014, near Papua New Guinea. This meteor has been a source of controversy for years, with some researchers arguing it showed characteristics consistent with artificial materials. Whether that's true or not, the data should be public. The fact that it apparently isn't raises questions about what else might be tucked away in NASA's databases. The 6th and final request addresses a broader concern that cuts to the heart of scientific transparency. Luna notes that inconsistent locations are listed separately in the fireball and light curve tables, and she calls for clarification and full release of this information to ensure transparency for the scientific community. On the surface, this sounds technical and mundane. But what it really means is that NASA's own internal data shows discrepancies that haven't been explained publicly. When you're tracking objects entering Earth's atmosphere, precise location data matters enormously. If that data conflicts between different measurement systems, scientists need to know why. Read as a whole, Luna's letter constructs a careful argument. It doesn't scream conspiracy or cover-up. It doesn't use inflammatory language or make wild accusations. Instead, it builds a case through specificity, through the accumulation of particular requests that together paint a picture of an agency that isn't living up to its stated commitment to open science. The letter thanks NASA for its continued leadership in advancing the frontiers of discovery, a diplomatic touch that makes the underlying criticism all the more pointed. We appreciate what you do, the letter seems to say, which is exactly why we're confused about why you're not doing it now. But here's what makes this letter genuinely unprecedented. NASA faces congressional inquiries all the time. Budget questions, mission priorities, safety reviews, these are routine. What's not routine is a sitting member of Congress formally requesting the release of specific scientific data about a particular object, backed by named scientists who are being denied access in the immediate aftermath of those scientists going public with accusations of stonewalling. This isn't oversight, this is intervention. The letter also represents something larger than just this one object, this one set of images. It's a test case for how transparent NASA really is when the stakes get weird, when the object in question isn't behaving quite like anything we've seen before, when respected scientists are asking uncomfortable questions about whether it might be artificial. Does NASA's commitment to open data hold when the data might fuel speculation about extraterrestrial technology? Luna's letter forces that question into the open. And the timing. Remember the timing. Luna's letter went public on October 31st. 3I-ATLAS reached its closest point to the Sun, its perihelion, on October 29th. That means this letter arrived right as the object was emerging from behind the Sun, right as observatories around the world were preparing to reacquire it, right as the critical observation window was opening. If 3I-ATLAS did something unusual during perihelion, if it manoeuvred or released smaller objects or showed any sign of non-natural behaviour, we would start seeing evidence in early November. Luna's letter lands precisely at the moment when NASA would be processing any such data. Coincidence? Maybe. Or maybe a congresswoman and a Harvard astrophysicist understand political timing as well as orbital mechanics. What we don't have yet, as of November 1st, is NASA's response. The agency hasn't released a statement about Luna's letter. The high-rise images remain unreleased. The supplementary Mars data, if it exists, stays locked away. And that silence itself tells a story. When a member of Congress formally requests scientific data that should already be public, and NASA doesn't immediately comply, or at least explain why compliance is delayed, something unusual is happening. Either there are legitimate bureaucratic or technical reasons for the delay, reasons that NASA will eventually articulate, or there's something else going on, something that makes the agency hesitant to open these particular files. Loeb has his own theory about the silence, and it's actually more generous than you might expect. In his Medium post about Luna's letter, he writes that he believes the recent delay in the dissemination of data from NASA as a result of the government shutdown does not flag extraterrestrial intelligence, but rather terrestrial stupidity. That phrase, terrestrial stupidity, has become something of a catchphrase for Loeb. It's his way of saying that bureaucratic incompetence is a more likely explanation than deliberate conspiracy. But here's the thing about that framing. Whether the delay is stupid or strategic doesn't actually matter to the scientists who need the data. Either way, they can't do their work. Either way, the public doesn't get to see what their tax dollars paid to observe. The government shutdown Loeb mentions is real, by the way. The US government entered a shutdown on October 1st, 2025, right as 3I-ATLAS was making its approach toward Mars. NASA was affected, with furloughs and suspended operations across various departments. But here's what makes the shutdown explanation incomplete. The shutdown didn't prevent NASA from releasing any data. The agency's public archives, the systems that automatically post images and scientific results, those kept running. What the shutdown affected was staffing, the human beings who process and verify and approve releases. So yes, the shutdown probably slowed things down, but 4 weeks? For images that should have been automatically released? That's where the explanation starts to fray. And there's another dimension to this that Luna's letter touches on but doesn't fully explore. Representative Luna specifically asks about unusual activity detected near Mars. Not just images of 3I-ATLAS itself, but signs of anything strange happening in Mars' orbit or atmosphere around the same time. What could that mean? One possibility, and this is speculation but informed speculation, is that NASA's Mars assets picked up something unexpected. Maybe increased radiation, maybe anomalous magnetic field readings, maybe something the rovers or orbiters detected that didn't fit expected parameters. If that happened, if there was any data suggesting 3I-ATLAS affected Mars in ways a normal comet shouldn't, NASA would be in a difficult position. Release that data and fuel speculation about artificial origins. Sit on it and risk exactly what's happening now, accusations of cover-up. This is where Loeb's advocacy connects to something bigger than just one object. For years, he's been arguing that the scientific establishment treats the possibility of extraterrestrial technology with irrational hostility, that perfectly legitimate hypotheses get shut down not because of evidence but because of stigma. When he proposed that Oumuamua, the first confirmed interstellar visitor back in 2017, might be artificial, the backlash was immediate and intense. Colleagues called him irresponsible. Some questioned his judgment. The fact that he's now chair of Harvard's astronomy department and director of the Galileo project, a major initiative to search for signs of extraterrestrial technology, suggests the criticism didn't stick. But it did establish a pattern. Loeb pushes boundaries. Loeb asks uncomfortable questions, and institutions push back. What's different this time is that Loeb isn't alone. He has a member of Congress backing his request for transparency. He has the world's biggest podcast amplifying his message to tens of millions of listeners. And most importantly, he has a case that's harder to dismiss. The high-rise images either exist or they don't. If they exist, NASA should release them. If there's a reason not to, NASA should explain that reason. Luna's letter makes that simple equation public and official. But let's zoom out for a second and consider what this moment represents. We have an interstellar object, only the third ever detected, behaving in ways that puzzle even mainstream astronomers. We have a Harvard scientist with impeccable credentials suggesting it might be artificial, not as his primary hypothesis, but as a possibility that shouldn't be dismissed without evidence. We have that scientist being denied access to data that should be public, and we have a member of Congress intervening to demand transparency. This isn't how science usually works, but maybe it's how science needs to work when the questions get this strange, when the stakes get this high, when the usual channels of academic discourse and peer review move too slowly for the timeline imposed by an object racing through our solar system. There's a phrase in Loeb's writing that keeps appearing, and it showed up again in his description of Luna's letter. He calls her support visionary. Not helpful, not appreciated, but visionary. That's a specific word choice. Vision implies seeing something others don't, understanding implications that aren't immediately obvious. What vision does Loeb see in Luna's intervention? Perhaps it's this. The question of whether we're alone in the universe is too important to leave entirely to scientists working within institutional constraints. It requires political will, public engagement, a willingness to push past the comfortable assumptions that keep research funding flowing and careers advancing. Luna's letter represents a politician willing to stick her neck out on a topic that most of her colleagues would run from. That takes vision. It also takes courage, because if 3I-ATLAS turns out to be a completely ordinary comet, if all these anomalies resolve into natural explanations, Luna will have spent political capital on what some will call a wild goose chase. But here's the counter-argument, and it's one that Loeb makes explicitly. The cost of investigating and being wrong is minimal. We spend some time, some telescope hours, maybe some mission extensions for Juno. The cost of not investigating and being wrong is catastrophic. If 3I-ATLAS is artificial, if it's some kind of reconnaissance probe or explorer from another civilization, and we fail to study it thoroughly because we were afraid of looking foolish, we'll have squandered the opportunity of the millennium. Luna's letter acknowledges this asymmetry. The requests she makes are specific, achievable, and relatively inexpensive. The potential payoff, even if the odds are low, justifies the effort. So where does that leave us as November begins? We have a formal congressional request for data. We have growing public awareness, thanks to the Joe Rogan podcast, that something unusual is happening with NASA's handling of 3I-ATLAS information. We have the object itself emerging from behind the sun, becoming observable again after weeks of solar conjunction, and we have a scientific community that's now watching very carefully to see not just what 3I-ATLAS does, but how NASA responds to the pressure for transparency. The next few weeks will reveal a lot. If NASA releases the high-rise images and they show something extraordinary, Luna's intervention will look prescient. If they show a completely normal cometary nucleus with expected outgassing, the calls for transparency will still be vindicated because scientists will have the data they need. The only outcome that would be truly problematic is continued silence, continued delay, a continued refusal to explain why data that should be public remains locked away. And here's something most people don't realise. Luna's letter isn't just about 3I-ATLAS. Look at Request 5 again, the one about the interstellar meteor database. That's asking NASA to open up historical data on multiple objects, to establish precedent for transparency about interstellar visitors in general. If NASA complies with that request, it sets a standard. Future interstellar objects, and there will be future ones as sky surveys get better, will have a clearer path to public data release. Scientists won't have to wait weeks or months or go through congressional representatives to access information about objects entering our solar system from beyond. That's the lasting impact Luna's letter could have, regardless of what 3I-ATLAS turns out to be. There's also a subtle point in the letter that deserves attention. When Luna mentions encouraging NASA to fund additional Juno observations, she's not just asking for telescope time, she's asking for radio observations specifically. Why does that matter? Because if 3I-ATLAS were transmitting any kind of signal, radio frequencies would be the most likely band. Comets don't emit radio signals in structured ways. They produce some radio noise from ionized gas, but nothing that would look like communication. If Juno's radio instruments detected anything unusual, Anything that showed patterns or structure or frequency characteristics inconsistent with natural processes, that would be significant regardless of whether it constituted actual communication. Luna's letter specifically highlights this capability, which suggests someone, probably Loeb, educated her about exactly what to ask for. This is tactical science advocacy at its finest. Don't just say we need more data, say we need this specific instrument to look at this specific frequency range during this specific time window. Make the request so precise that NASA can't respond with vague promises of future observations. Either Juno can do it or it can't. Either NASA funds the mission extension or it doesn't. The specificity removes wiggle room, and that brings us back to where we started, with a letter dated October 31st arriving at NASA headquarters just as 3I-ATLAS completes its perihelion passage. In the old model of space science, NASA would process the data at its own pace, maybe releasing preliminary findings weeks or months later once everything was verified and peer-reviewed and properly formatted. In the new model, shaped by social media and podcast culture and public demand for real-time information, that timeline doesn't work anymore. People want to know what's happening now, not after some editorial committee signs off on it. Luna's letter acknowledges that new reality. It says we can't wait for the usual process, not when the object might be gone before you finish your internal review. So Representative Anna Paulina Luna did something unprecedented. She took the conversation about 3I-ATLAS out of academic journals and into congressional record. She transformed Avi Loeb's frustrations from podcast complaints into official government requests. She put NASA in a position where silence is no longer an option, where the agency has to either release the data or explain publicly why it can't. That's not how science usually interfaces with politics. But then again, we've never had anything quite like 3I-ATLAS before. An object massive enough to see from Earth, fast enough to confirm interstellar origin, weird enough to make even conservative astronomers uncomfortable, and now important enough that Congress is paying attention. The letter that shook NASA is still reverberating. The response, or lack of response, will tell us something important about how our institutions handle the possibility, however remote, that we might not be alone. Harvard versus NASA, the Joe Rogan Showdown. October 28th, 2025. Studio somewhere in Austin, Texas. Avi Loeb sits down across from Joe Rogan for what will become one of the most consequential podcast episodes in the history of scientific discourse. 2 hours and 15 minutes of conversation that would force NASA into a defensive position, trigger congressional intervention, and bring the 3I-ATLAS controversy into the mainstream consciousness. But the real story isn't just what Loeb said, it's how he said it, the precision of his accusations, the evidence he brought, and the institutional response that never came. Loeb didn't waste time with pleasantries. Within the first 10 minutes, he laid out the central accusation. NASA's high-rise camera aboard the Mars Reconnaissance Orbiter captured images of 3I-ATLAS on October 2nd and 3rd when the object passed within 30 million kilometers of Mars. Those images, Loeb stated flatly, were never released. Not delayed, not pending review, never released. The distinction matters because it shifts the conversation from bureaucratic slowness to active suppression. Rogan, to his credit, understood the implications immediately. You're telling me NASA took pictures of this thing and just didn't share them? The question hung in the air for a beat before Loeb delivered the detail that would go viral within hours. I wrote to the principal investigator of HiRise, Loeb said, his voice carrying the measured frustration of someone who's exhausted diplomatic channels. I wrote asking, can I get the data? I'm a scientist. I need this for my research. The response? Loeb paused for effect. No response. Nothing. Complete silence. Think about what that means in the context of modern astrophysics. The HiRise principal investigator isn't some low-level technician. This is one of the most prestigious positions in planetary science, overseeing one of the most powerful cameras ever sent to another planet. When a Harvard professor, former chair of the astronomy department, director of multiple research initiatives, writes requesting data that should be publicly available, getting no response isn't normal. It's not an oversight. It's a choice. Rogan pressed on the timing. This was how long ago? 4 weeks, Loeb replied. 4 weeks of nothing. And here's where Loeb's presentation became particularly damaging to NASA. He didn't speculate wildly about conspiracies or cover-ups. Instead, he offered what he called the most likely explanation. It's much more likely, Loeb said, not to be related to extraterrestrial intelligence, but to terrestrial stupidity. That phrase landed like a hammer. Terrestrial stupidity. It became the soundbite that defined the episode, the quote that spread across social media, the framing that made NASA's silence look worse than any conspiracy theory could. Because here's the thing, calling it stupidity is actually more damaging than calling it malice. Malice would imply intentionality, purpose, some grand strategy to hide evidence. Stupidity implies institutional dysfunction, an agency so tangled in its own bureaucracy that it can't perform the basic function of scientific transparency, even when a major researcher formally requests data. If you're NASA, you almost want to be accused of conspiracy because at least that suggests competence. Being called stupid by one of Harvard's most prominent astrophysicists on the world's biggest podcast, that's harder to recover from. But Loeb didn't stop with the high-rise images. He walked Rogan through what those images would show and why they matter more than anything Hubble or Webb have captured. The spatial resolution, Loeb explained, would be approximately 30 kilometers per pixel. Rogan, not being an astronomer, needed context. Is that good? It's 3 times better than our best Hubble image, Loeb replied. But more importantly, it's a different angle. Hubble saw 3I-ATLAS nearly edge-on, Earth and the Sun separated by only about 10 degrees relative to the object. The high-rise view would be sideways, perfect for understanding the geometry of whatever's creating that glow around the nucleus. This is where Loeb's scientific credibility became crucial. He wasn't just complaining about not getting data, he was explaining exactly why that specific data from that specific instrument at that specific time mattered scientifically. The glow around 3I-ATLAS, visible in earlier images, shows an unusual geometry. It's not symmetric like you'd expect from a comet's coma. It has structure, directionality. The technical term Loeb used was anti-tail, a jet of material pointing toward the sun rather than away from it. Normal comets don't do that. Solar radiation pushes material away from the sun, creating tails that stream behind the comet as it moves. 3I-ATLAS shows something different, and the Mars perspective would have revealed exactly what that geometry looks like from the side. Rogan, sensing this was important, asked the obvious question: what could cause that? And here's where Loeb demonstrated why he's both celebrated and controversial. He gave the natural explanation first. Cometary jets, he said, can sometimes appear to point sunward due to the geometry of gas release and the comet's rotation. Dust particles of different sizes respond differently to solar radiation pressure, creating complex tail structures. These are known phenomena documented in many comets. But then Loeb added the qualifier that makes his colleagues uncomfortable. However, he said, if you were designing a spacecraft that needed to decelerate as it approached the sun, you'd fire your engines in the direction of travel. That would create a jet pointing roughly sunward. The visual signature would be similar. This is Loeb's method, and it's worth understanding because it's central to why this controversy has legs. He doesn't lead with the alien hypothesis. He presents the conventional explanation, shows its limitations, then introduces the technological alternative not as likely, but as something we can test. The high-rise images would help test it. If the anti-tail structure showed characteristics consistent with cometary outgassing, periodic variations matching the nucleus rotation, asymmetries explainable by local variations in surface composition, then the natural explanation would be strengthened. If instead the structure showed continuous, directed emission, with no obvious connection to solar heating patterns, that would be interesting. That would require further investigation, but we can't do any of that investigation without the images. That was Loeb's core argument. NASA isn't just failing to release data that might support an exotic hypothesis. They're failing to release data that would help scientists rule out that hypothesis. If you genuinely think 3I-ATLAS is just a comet, Loeb argued, you should be eager to release every image, every spectrum, every data point that confirms normal cometary behavior. The fact that NASA isn't doing that, whether through malice or stupidity, undermines the scientific process. Rogan then shifted to a question that many in his audience were probably thinking. Why would NASA hide this if it really was alien? What's the logic? Loeb's response revealed a more nuanced understanding of institutional behavior than conspiracy theorists usually muster. I don't think it's a deliberate cover-up in the sense of some secret committee deciding to hide evidence, Loeb said. I think it's cultural. The scientific establishment has a deep resistance to taking the possibility of extraterrestrial technology seriously. That resistance manifests in peer review, in editorial decisions, in funding priorities, and yes, in decisions about what data gets released when. He then shared something that hadn't been widely reported. Loeb revealed that he'd submitted a paper on 3I-ATLAS for publication, a paper analysing its unusual trajectory and suggesting that the trajectory's rare characteristics, its alignment with the ecliptic plane, its close approaches to multiple planets, might indicate design rather than random arrival. The paper was technically sound. The math was solid. The statistical analysis showing how unlikely this trajectory is for a random interstellar object was rigorous. But the editor, Loeb said with audible frustration, refused to publish unless he removed a single sentence from the conclusion. "What sentence?" Rogan asked. "The sentence suggesting that the trajectory might have been targeting the inner solar system by design," Loeb replied. The editor said the rest of the paper was fine, the analysis was acceptable, but that one sentence had to go. Why? Because it implied intelligent design. Because it crossed the line from observational astronomy into speculation about alien technology. Never mind that the sentence was clearly labelled as one possible interpretation. Never mind that considering alternative hypotheses is literally how science is supposed to work. That sentence made the editor uncomfortable, so it had to be removed. This revelation struck a chord with Rogan's audience because it confirmed a suspicion many of them already held, that mainstream science has gatekeepers who filter out ideas that challenge accepted frameworks. Loeb didn't have to argue that point explicitly, he just had to present the facts. Solid paper, peer-reviewed analysis, one sentence suggesting a testable hypothesis about artificial origin. Editor demands removal. Publication requires compliance. That sequence of events speaks for itself. But here's where Loeb's argument became truly compelling. He pointed out that this kind of gatekeeping affects not just unusual hypotheses, but the pace of discovery itself. How many times in history, he asked, has the scientific consensus been wrong? How many times have we later learned that the dismissed theory, the controversial idea, the hypothesis that couldn't get published because it made editors uncomfortable, turned out to be correct? Copernicus, Wegener and continental drift, the initial resistance to the Big Bang theory. The list is long and humbling, and the cost of being wrong cuts both ways. If scientists dismiss the possibility that 3I-ATLAS is artificial, and it turns out to be natural, they've wasted some time and telescope resources. Embarrassing perhaps, but not catastrophic. If scientists dismiss the possibility that it's artificial, and it turns out to be a reconnaissance probe from another civilization, they've squandered the opportunity of human history. The asymmetry is stark. Conservative caution isn't the safe choice when the stakes are this high. Rogan, clearly engaged now, asked what Loeb thought 3I-ATLAS actually was. And here Loeb demonstrated the scientific honesty that sets him apart from both true believers and rigid skeptics. As of now, he said carefully, 3I-ATLAS appears most likely to be a natural comet. The composition we've measured, carbon dioxide ice, some water, organic compounds, that's all consistent with a cometary origin. The anti-tail, while unusual, has precedent in other comets. The rapid rotation, the brightness variations, these can all be explained by natural processes. But, and this is crucial, we have anomalies that don't fit comfortably into the standard comet model. He then listed them, and this list would become central to later discussions. First, the trajectory, aligned to within 5 degrees of the ecliptic plane with a random probability of only about 0.2%. Second, the close approaches, coming within tens of millions of kilometers of Mars, Venus and Jupiter, with a combined probability around 0.005%. Third, the mass. If the non-gravitational acceleration measurements are correct, 3I-ATLAS must be far more massive than typical comets, somewhere around 33 billion tons. Fourth, the composition. Nickel emissions without corresponding iron, something almost never seen in natural objects. Fifth, the polarization. Negative polarization more extreme than any known comet. Sixth, the timing. Reaching perihelion precisely when it's hidden from Earth-based telescopes, optimal for maneuvers if it were artificial. Each anomaly alone might be dismissed as unusual but not impossible. Together they form a pattern that at least deserves investigation without prejudice. That was Loeb's point. Not that 3I-ATLAS is definitely artificial, not even that it's probably artificial, just that the possibility shouldn't be dismissed before we have all the data, and we can't have all the data if NASA won't release it. The conversation then turned to what Loeb called the October 29th test. 3I-ATLAS would reach perihelion, its closest approach to the Sun, on that date. Perihelion is significant for spacecraft because of something called the Oberth effect. When you fire a rocket engine, you get more kinetic energy change if you fire it when you are already moving fast. At perihelion, 3I-ATLAS would be moving at its maximum velocity, around 68 kilometers per second. If it were a spacecraft that needed to adjust its trajectory, release smaller probes, or execute any kind of maneuver, perihelion would be the time to do it. The energy efficiency gains are enormous. And here's the coincidence that bothers Loeb. 3I-ATLAS reaches perihelion on October 29th. It reaches solar conjunction, the point where it's directly behind the Sun as seen from Earth, on October 21st. Those dates are 8 days apart, which means the object is hidden from Earth-based observation during the optimal window for spacecraft operations. If you were designing an interstellar probe's trajectory, Loeb argued, you'd want to do your perihelion maneuvers away from the prying eyes of any civilizations that might be watching. Was this planned? Probably not. But possibly. We can't rule it out without evidence, and we can't gather evidence if we can't observe the object during that critical window. That's why, Loeb explained, he wanted the high-rise images so badly. Mars-based observations on October 2nd and 3rd caught 3I-ATLAS just before it disappeared behind the Sun. Those images are the last clear look anyone got before perihelion. If there was any change in the object's structure, any separation of components, any evidence of non-natural activity, those images would show it. And if they show nothing unusual, that's valuable too. Either way, the scientific community needs to see them. Rogan asked the question his audience was thinking. So what do you do now? NASA won't respond, you can't get the data, you've got all these questions and no way to answer them. Loeb's response was immediate. I go public. I talk to congresspeople. I come on podcasts like this one. I write articles. I make enough noise that NASA has to respond, either by releasing the data or by explaining publicly why they won't. And if the explanation is legitimate, fine. Maybe there are technical issues with the images, maybe there are calibration problems, maybe there's some reason I'm not aware of that makes immediate release difficult, but they need to say that. Silence isn't acceptable when the questions are this important. The timing of the podcast, 3 days before Luna's letter, suggests Loeb's strategy worked faster than even he expected. Going on Joe Rogan isn't a typical move for a Harvard astrophysicist. It's not how you advance your academic career or secure grant funding, but it's how you reach millions of people, including apparently people with political power, who can force institutional responses that peer-reviewed papers never could. Whether you view that as a corruption of the scientific process or an evolution of it probably depends on your perspective, but it's undeniably effective. As the episode wound down, Loeb made one more point that deserves attention. He talked about cosmic modesty, the idea that we should approach the question of extraterrestrial intelligence with humility rather than certainty. We don't know if we're alone, he said. We don't know if technological civilizations are common or rare. We don't know if interstellar travel is feasible for advanced species. We don't even know what forms intelligence might take at scales beyond human comprehension. All we can do is look at the evidence without prejudice, follow it wherever it leads, and admit when we don't know something. That's not the scientific establishment's strong suit, Loeb said, with what might have been a smile. We're much better at defending what we think we know than at acknowledging the vastness of what we don't. The episode ended without resolution, without NASA's response, without definitive answers about what 3I-ATLAS really is. But it accomplished something arguably more important. It moved the conversation about this object from academic journals that few people read into the cultural mainstream. It gave millions of listeners a framework for understanding why the data matters, why transparency is crucial, why institutional resistance to uncomfortable questions undermines the scientific enterprise itself. And it set the stage for what came next. A congresswoman picking up where a podcast left off, transforming Loeb's frustrations into formal government action. Within hours of the episode going live, clips spread across social media. The terrestrial stupidity line became a meme. The accusation that NASA was withholding data trended on multiple platforms. And somewhere in Florida's 13th District, Representative Anna Paulina Luna apparently decided this was worth getting involved in. The Joe Rogan episode didn't just document the controversy, it catalyzed it, forcing the next phase of what was becoming less a scientific debate and more a public reckoning with how we handle the possibility of contact. The data embargo deepens October 1st, 2025. The United States government enters a shutdown, not a slow bureaucratic grinding to a halt, but an immediate cessation of non-essential operations across federal agencies. NASA employees are furloughed. Mission control operations continue. Spacecraft don't stop needing guidance just because Congress can't pass a budget, but everything else pauses. Press releases, public outreach, data processing and release, all suspended pending resolution of the budget impasse. It's a familiar ritual in American politics, frustrating but predictable. Except this time, the shutdown arrives with timing so precise, it almost strains credulity. October 3rd, 2025. 3I-ATLAS makes its closest approach to Mars, 30 million kilometers separating an interstellar visitor from the red planet, close enough that multiple Mars orbiters can observe it with unprecedented resolution. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter train their instruments on the object, NASA's Mars Reconnaissance. Orbiter, with its powerful high-rise camera, captures what should be the clearest images yet obtained. And then, nothing. Days pass. Weeks pass. The usual data pipeline, the automatic releases that have become standard in the era of open science, stays dry. Now here's where careful analysis becomes crucial, because the easy narrative is that the government shutdown explains everything. NASA was understaffed, data processing was delayed, these things happen during shutdowns. But that explanation doesn't actually hold up under scrutiny. NASA's data archives, the servers and automated systems that host images from Mars missions, those kept running. They're considered essential infrastructure. The Mars Reconnaissance Orbiter has been sending images back to Earth for years, and those images typically appear in the public archive within days, sometimes hours. The process is largely automated. A human being needs to verify the image quality, add metadata, maybe flag anything particularly interesting. But the core pipeline doesn't require active staffing to function. So when people say the shutdown explains the delay, what they're really saying is that human decision makers, the ones who approve releases or prioritize processing, weren't available. And that raises an interesting question. If the system is designed to be mostly automatic, why would this particular set of images need special human intervention? What about the high-rise observations of 3I-ATLAS required active decision-making that prevented their automatic release? One possibility, and this is the generous interpretation, is that the images showed something unexpected, and NASA wanted expert analysis before making them public. Not a cover-up, but due diligence. If the images revealed something that didn't match the preliminary comet classification, releasing them without context could cause unnecessary confusion or alarm. Better to wait until scientists can provide proper interpretation. That's standard practice for anomalous observations. The problem with this explanation is that it contradicts NASA's stated protocols. The agency has repeatedly emphasized that raw data should be released regardless of what it shows, with scientific interpretation following in papers and press releases. Holding back raw images to prevent misinterpretation isn't how the system is supposed to work. Another possibility is more technical. Maybe there were calibration issues with the high-rise observations. Maybe the pointing wasn't quite right, or atmospheric conditions on Mars affected the images, or some technical glitch made the data difficult to process. These things happen, especially for targets of opportunity, like 3I-ATLAS, where observations have to be scheduled quickly, without extensive planning. If the images were too low quality to be scientifically useful, NASA might reasonably decide to prioritize other data processing tasks. But here's the problem with that theory. Loeb's correspondence with the high-rise principal investigator, or rather his lack of response to that correspondence, suggests the images exist and are of sufficient quality to be worth looking at. If they were just garbage data, a quick email saying sorry, the observations didn't work out would have ended the controversy. So we're left with a third possibility that makes institutional sense, even if it doesn't reflect well on NASA's transparency. The images exist, they're scientifically valuable, but releasing them during a government shutdown when public affairs staff weren't available to manage the messaging felt risky. Better to wait until normal operations resumed, when press releases could be carefully crafted, when scientists could be lined up for interviews, when the narrative could be controlled. This is bureaucratic thinking, not scientific thinking. It treats data as something to be managed rather than shared. and it's precisely the kind of institutional behaviour that fuels suspicion. But the high-rise images are just the most visible tip of a much larger data iceberg. Consider what else should have been released by early November. The European Space Agency's Mars Express used its high-resolution stereo camera, its Omega spectrometer, and its SPICAM atmospheric instrument to observe 3I-ATLAS during the October 1st through 7th window. Those are sophisticated instruments capable of measuring composition, temperature, gas production rates, all kinds of detailed information about what this object is made of and how it's behaving. ESA announced the observations would happen. They confirmed the spacecraft successfully targeted 3I-ATLAS. And then, like NASA, they went quiet. ExoMars' Trace Gas Orbiter also observed using its colour and stereo surface imaging system, its infrared spectrometer, and its atmospheric chemistry suite. Same story. Observations announced, targeting confirmed, data not released. China's Tianwen-1 orbiter and the UAE's Hope orbiter, both at Mars during this window, also had the opportunity to observe. Whether they did, and what they might have seen, remains undisclosed. This coordinated silence across multiple space agencies starts to look less like bureaucratic delay and more like policy. And that raises uncomfortable questions. Did NASA communicate with ESA and other partners about holding back data until some threshold of analysis was complete? Is there an informal agreement among space agencies about how to handle observations of unusual interstellar objects? Or are multiple agencies independently deciding that these particular observations warrant extra caution before release? There's a precedent that's worth considering. Here. When Oumuamua was discovered in 2017, the first interstellar object ever detected, data flowed relatively freely. Observatories around the world shared their measurements. Papers analysing the object's trajectory, composition and characteristics appeared rapidly. Loeb's controversial paper, suggesting it might be artificial, was published in a peer-reviewed journal, not suppressed or delayed. The scientific process worked more or less as designed. So what's different this time? 3I-ATLAS is bigger, for one thing. Much bigger. Oumuamua was tiny, maybe a few hundred meters across, and it wasn't particularly bright. By the time we knew it was interesting, it was already leaving the solar system. We got a few weeks of observations, learned what we could, and then it was gone. 3I-ATLAS is orders of magnitude more massive, bright enough to study for months, and on a trajectory that brings it close to multiple planets. There's time to observe it properly, time to gather extensive data, time to make measurements that could actually test the natural versus artificial question. That extended observation window might be precisely why agencies are being more cautious, or consider the public attention factor. Oumuamua became a big story, but mostly in retrospect. By the time mainstream media picked up on Loeb's artificial origin hypothesis, the object was long gone. There was no immediacy, no sense that humanity needed to do something right now while the object was still accessible. 3I-ATLAS is different. It's here now, observable now, potentially reachable by existing spacecraft if we act quickly. The public pressure is greater, the scrutiny more intense, and maybe space agencies decided that requires a different communication strategy. But let's talk about what we do know happened, because there's one release that makes the overall silence more puzzling. On October 5th, NASA quietly posted images from the Perseverance rover's navigation cameras. These aren't science-quality images. Navcam is designed to help the rover avoid obstacles, not to do astronomy. But on October 3rd, someone at Mission Control apparently thought to point one of those cameras at the sky and capture 3I-ATLAS. The resulting images show a faint streak against the background stars. Not much detail, certainly nothing approaching the resolution HiRISE could achieve, but proof that Perseverance did observe the object. Why release the Navcam images but not the HiRISE images? The most charitable explanation is that Navcam data goes through a different pipeline, one that's more automated and less subject to human gatekeeping. The images appeared in the public archive because that's just what happens with Navcam data by default. Nobody thought to hold them back because they don't show much anyway. But that explanation, while plausible, highlights the inconsistency. If the policy is to release all data automatically, HiRISE images should have appeared too. If the policy is to hold back data pending review, Navcam images should have been held as well. Loeb seized on those Navcam images when they appeared. He analysed them, extracted what information he could about 3I-ATLAS's brightness and position, and published his findings in a Medium post. His point wasn't that the Navcam images revealed anything particularly exciting. It was that they proved Perseverance was looking at 3I-ATLAS on October 3rd, which meant Mars Reconnaissance Orbiter almost certainly was too, which made the absence of high-rise images even more conspicuous. You can't claim the observations didn't happen when we have navcam images from the same day. There's another dimension to this that deserves attention. Luna's letter specifically asks about unusual activity detected near Mars around the time of the 3I-ATLAS flyby. Not just images of the object itself, but any anomalies in Mars' orbit or atmosphere that coincided with its passage. This is subtle but important language. It suggests the possibility that Mars assets detected something beyond the expected cometary signature. Maybe increased radiation levels, maybe disturbances in the local magnetic field, maybe particle detections that didn't fit expected patterns. If that happened, if any Mars instrument recorded something anomalous during the October 3rd flyby, NASA would face a genuine dilemma. Release the data and invite speculation that might not be scientifically justified. Sit on it and risk accusations of cover-up. There's no good option. But the current approach, releasing nothing and explaining nothing, might actually be the worst option because it allows speculation to run wild without any facts to constrain it. And here's what makes the timing so suspicious to observers. The government shutdown began on October 1st. 3I-ATLAS approached Mars on October 3rd. By the time normal operations might have resumed, the object was already heading towards solar conjunction, disappearing behind the Sun from Earth's perspective. The window for ground-based observational campaigns effectively closed. So even if NASA had wanted to coordinate a comprehensive study involving multiple observatories to contextualize whatever the Mars assets found, that opportunity was lost. Whether by design or accident, the shutdown timing created a gap in the observational record exactly when the object was doing something potentially interesting. Loeb's phrase, terrestrial stupidity, captures this perfectly. You don't need a conspiracy if bureaucratic ineptitude achieves the same result. A shutdown that wasn't planned with 3I-ATLAS in mind nevertheless arrived at the worst possible moment for transparency. Data processing systems that usually work smoothly hit roadblocks precisely when they needed to work faster. Communication channels that should facilitate scientific collaboration went silent at the critical juncture. Is that a cover-up or just Murphy's Law operating at scale? Hard to say, but from the perspective of scientists trying to study an unprecedented object, the distinction doesn't matter much. There's also the question of what ESA knows and isn't saying. Mars Express and ExoMars Trace Gas Orbiter are European spacecraft, not subject to US government shutdowns or NASA's internal politics. The European Space Agency has its own data release protocols, its own scientific culture, its own pressures and priorities. When ESA goes quiet at the same time NASA does, that suggests either coordination or parallel decision-making based on similar concerns. Either way, it's striking. On October 29th, after weeks of silence, ESA finally released a brief statement. Confirming observations had been made, mentioning that data was being processed. Promising results would be shared once analysis was complete. No timeline, no specifics about what instruments were used or what preliminary findings might be. Just enough to acknowledge the observations happened without actually revealing anything. It was a masterclass in saying nothing, while appearing to say something. And that brings us back to the core question. What could these images and measurements possibly show that would justify this level of caution? If 3I-ATLAS is behaving exactly like a comet should behave, there's no reason to delay. The data would support the conventional interpretation and put exotic hypotheses to rest. If the images show clear evidence of artificial structure, well, that's obviously worth being careful about, but holding it back indefinitely doesn't serve anyone. The only scenario where this extended delay makes sense is if the data is ambiguous, showing things that don't quite fit the comet model, but don't definitively prove artificial origin either. Ambiguous data is actually the hardest case for space agencies to handle. Clear results, either way, have obvious communication strategies. But what do you do when the best images you've ever obtained of an interstellar object show structure that might be jets of cometary gas or might be something else? Composition that's unusual but not impossible for natural objects, behaviour that's anomalous but not definitively artificial. You can't call a press conference and say we don't know what this is. That creates more confusion than clarity. But you also can't sit on the data forever. Eventually scientists need to see it so they can debate and analyse and test hypotheses. We're now a month past the Mars observations, approaching the December 19th closest approach to Earth, and still nothing official beyond those navcam images. That's not normal. That's not how the system is supposed to work, and whether it's stupidity or strategy, the effect is the same. Scientists who could be analysing this data are instead speculating about why they can't access it. Public interest that could be channeled into scientific understanding is instead feeding conspiracy theories. And an opportunity to demonstrate transparency in the face of extraordinary circumstances is being squandered one silent day at a time. The data embargo deepens not because new restrictions are being added, but because time keeps passing and the restrictions that shouldn't exist in the first place remain in effect. Every day without release is another day of questions, another day of institutional credibility eroding, another day that the gap between what NASA says about transparency and what NASA does about transparency grows wider, and the clock is ticking toward December 19th when 3I-ATLAS makes its closest approach to Earth, and hundreds of telescopes will be pointed at it gathering new data that might make these withheld observations look even more significant in retrospect, or might finally provide the context that explains why they were worth waiting for. Academic censorship, the editor's ultimatum. The paper was solid. Avi Loeb knew it was solid because he'd been writing papers for 4 decades, hundreds of them, published in the most prestigious journals in astrophysics. This one analysed the trajectory of 3I-ATLAS with rigorous statistical methods, calculating the probability that an interstellar object would arrive aligned with the ecliptic plane the way this one did, computing the odds that random chance would bring it so close to Mars, Venus and Jupiter on a single pass through the inner solar system. The math was clean, the analysis was conservative, the conclusions followed logically from the evidence. It was, by any reasonable standard, publication ready. Then came the email from the editor. The paper is fine, the message said, or words to that effect. The technical content is acceptable, the methodology is sound, the statistics are properly calculated. But there's a problem. One sentence in the conclusion. The sentence that suggested the trajectory's unusual characteristics might indicate design rather than chance. That sentence, the editor explained, would need to be removed before publication could proceed. Stop and think about what that means for a moment. A peer-reviewed journal, ostensibly dedicated to advancing scientific knowledge, tells an accomplished researcher that his analysis is correct, but his interpretation is unacceptable. Not wrong, mind you. The editor didn't claim the interpretation was logically flawed or statistically unjustified, just that it crossed a line, that it violated some unwritten rule about what kinds of hypotheses are permissible in mainstream astrophysics. Remove the sentence about possible design and we'll publish your work. Keep the sentence and we won't. Loeb faced a choice. Comply and get the paper published, adding it to his long list of conventional academic achievements. Or refuse and make a point about scientific freedom, about the importance of considering all hypotheses that fit the data, about the damage that gatekeeping does to the search for truth. He chose to comply, at least initially, because getting the statistical analysis into the literature mattered. But he also went public about what happened, first in blog posts, then in interviews, and most dramatically on the Joe Rogan podcast. The editor might have controlled what appeared in the journal, but they couldn't control the larger conversation. What makes this incident particularly revealing is that Loeb wasn't proposing anything scientifically outlandish. He wasn't claiming 3I-ATLAS is definitely artificial. He wasn't even saying it's probably artificial. The offending sentence essentially said, given these unusual trajectory characteristics, one possibility worth considering is that they might result from design. That's conditional language, speculative language, the kind of language scientists use all the time when discussing hypotheses that require further testing. If the trajectory had shown characteristics suggesting a collision in its past, nobody would object to a sentence saying these features might indicate impact history. But suggest the features might indicate intelligent design, and suddenly it's unpublishable. This reveals something important about how science actually works, as opposed to how we like to imagine it works. The idealized version says scientists follow evidence wherever it leads, testing hypotheses without prejudice, welcoming challenges to accepted theories because that's how knowledge advances. The reality is that science is done by human beings embedded in institutions, with cultures, politics, and taboos. Some ideas are encouraged, some are tolerated, and some are actively discouraged through mechanisms that range from subtle social pressure to explicit editorial rejection. The taboo around extraterrestrial intelligence runs particularly deep. Partly this is historical. The field has been plagued by pseudoscience, wild speculation, and outright fraud. Serious scientists saw their colleagues damage their careers by association with UFO research or SETI projects that went nowhere. Over time, a protective mechanism developed. Distance yourself from anything that might be labelled fringe. Don't ask questions that sound too much like the kind of questions cranks ask. Play it safe. This is understandable as a sociological phenomenon, but it's terrible for science. Because here's what that taboo prevents. It prevents serious investigation of anomalous observations that might, however unlikely, indicate technology. It creates a self-fulfilling prophecy where we don't find evidence of extraterrestrial intelligence because we've made it professionally risky to look for it, or even to acknowledge ambiguous findings that don't rule it out. Loeb's paper didn't claim to have found alien technology. It just said, here's something unusual that we should study more carefully. And even that modest suggestion was too much for the editor to allow. The mechanism of censorship here is worth understanding, because it's subtle. Nobody told Loeb he couldn't publish his ideas. He wasn't fired or sanctioned or prevented from doing research. The editor simply said this particular sentence can't appear in this particular journal. Loeb remained free to post his ideas on Medium, to discuss them on podcasts, to present them at conferences. But those venues don't carry the same weight as peer-reviewed publication. When scientific debates happen, the currency is papers in respected journals. By preventing that one sentence from entering the formal literature, the editor effectively marginalised the hypothesis, making it easier for other scientists to dismiss. This is how institutional gatekeeping works in modern science. It's rarely overt censorship. It's more like applied friction. The hypothesis isn't forbidden, just made more difficult to advance through normal channels. You can talk about it, but not in ways that count for tenure decisions or grant applications. You can discuss it at conferences, but it won't help your career. You can mention it in popular media, but that might actually hurt your reputation among colleagues who value peer-reviewed publication above public engagement. The result is a system that filters out unconventional ideas not through debate and evidence, but through career incentives that reward conformity. And the editors who enforce these filters probably don't see themselves as censors. They see themselves as quality control, protecting the journal's reputation, maintaining standards, preventing the publication of material that might damage credibility. From their perspective, letting Loeb's paper include that sentence about possible design would invite criticism. Other scientists would question the journal's judgment. Reviewers would complain. The journal might be seen as giving legitimacy to speculation that most astronomers consider implausible. Better to have Loeb remove the sentence and avoid the controversy. But that logic has a fatal flaw. It assumes the editor knows which hypotheses are worth considering and which aren't, which interpretations are scientifically respectable and which are fringe. It assumes the current consensus about what's plausible is reliable, that the mainstream can't be wrong about fundamental questions. History suggests otherwise. Continental drift was fringe until it wasn't. The Big Bang was controversial until it wasn't. Heliocentrism got Galileo in serious trouble. The list of ideas that were initially dismissed or suppressed and later vindicated is long enough to inspire humility. Loeb made this point explicitly during his Rogan appearance. Science advances, he said, by considering possibilities that seem unlikely. If we only investigated hypotheses that fit comfortably within existing frameworks, we'd never discover anything genuinely new. The fact that extraterrestrial technology seems unlikely to most scientists doesn't mean we shouldn't look for evidence of it, especially when we have an object that shows multiple anomalies and is accessible to observation. The whole point of science is to let evidence decide, not to let editorial committees decide what evidence is worth gathering. There's another dimension to this that Loeb emphasised, the cost-benefit analysis, investigating 3I-ATLAS thoroughly and discovering its natural costs us what? Some telescope time, some mission extensions, maybe $15 million to keep Juno operating long enough to observe the object near Jupiter. That's rounding error in NASA's budget. But failing to investigate thoroughly and missing evidence of artificial origin would be catastrophic. We'd have squandered the chance to confirm we're not alone, to learn from technology potentially far more advanced than ours, to make the most important discovery in human history. The asymmetry is extreme. Conservative caution isn't the safe choice when the potential payoff is this large. Yet editorial gatekeeping enforces conservative caution by default. Papers that challenge accepted frameworks face higher burdens of proof. Hypotheses that sound exotic require more evidence than conventional interpretations, even when the evidence equally supports both. This might seem reasonable. Extraordinary claims require extraordinary evidence and all that, except it means we systematically underinvest in investigating possibilities that don't fit existing models. We're biased toward confirming what we already think we know. And here's where it gets personal for Loeb, in ways that shaped his willingness to fight this battle publicly. This isn't the first time he's faced editorial resistance to papers discussing possible artificial origin for astronomical objects. His work on Oumuamua encountered similar barriers. Papers suggesting Oumuamua's acceleration might result from a light sail rather than outgassing were harder to publish than papers assuming natural causes. The evidentiary standards were different, the scrutiny more intense, the editorial process more onerous. Eventually the papers got published, but with more difficulty than comparable work proposing conventional explanations. That double standard matters because it affects what research gets done in the first place. If you know papers proposing artificial origins will face uphill battles in peer review, while papers proposing natural explanations will sail through, what kind of research are you incentivized to do? You'll chase questions that lead to publishable papers, which means questions that yield conventional answers. The career structure of science, built around publication metrics and citations and funding success, pushes researchers towards safe topics and away from risky ones. Not through explicit prohibition, but through implicit pressure. Loeb is relatively immune to that pressure because he's already established, already tenured at Harvard, already recognized as a major figure in astrophysics. He can afford to take risks that a junior, researcher dependent on the next grant or tenure decision cannot. That's why he's become the public face of the push to take extraterrestrial technology seriously. Not because he's the only scientist who thinks we should look, but because he's one of the few in a position to say it without destroying his career. But even for Loeb, the gatekeeping has effects. The refuse sentence in his 3I-ATLAS paper is just one example. There are conference talks that didn't get accepted because program committees felt the topic was too controversial. There are grant applications that faced extra scrutiny because the proposed research touched on artificial origins. There are collaborations that didn't materialize because potential partners worried about association with work that might be seen as fringe. These aren't dramatic acts of censorship. They're death by 1,000 cuts, small barriers that accumulate to make certain kinds of research harder than they should be. And the tragedy is that this gatekeeping doesn't protect science from bad ideas. It protects scientists from good ideas they're not ready to accept. Bad ideas, ideas that are wrong in demonstrable ways, those get filtered out naturally through replication failures and contradictory evidence and the normal process of scientific debate. But potentially good ideas that challenge accepted frameworks need active investigation to determine whether they're right. Gatekeeping prevents that investigation by making it professionally costly. Consider what would happen if the editor had let that sentence stand. Other scientists would read the paper, evaluate the trajectory analysis, consider the suggestion about possible design, and either find problems with the reasoning or acknowledge it as a testable hypothesis worth investigating further. Some would disagree, writing response papers explaining why natural processes better explain the observations. Others would agree, proposing additional observations or analyses to test the hypothesis. That's how science is supposed to work. Debate in the literature, evidence accumulating on both sides, gradual convergence toward truth. Instead, by forcing removal of the sentence, the editor prevented that debate from happening in the formal scientific literature. The hypothesis exists now primarily in blog posts and podcasts, outside the peer review system, where it could be properly scrutinized and tested. Ironically, that makes it harder to evaluate scientifically. Loeb's critics can point to the lack of peer-reviewed papers supporting artificial origins as evidence the hypothesis isn't serious. But those papers don't exist partly because editors won't publish them, creating a circular logic that protects the status quo. There's also a broader cultural issue at play. Science is supposed to be international, transcending national and cultural boundaries. But the editorial gatekeeping Loeb describes is concentrated in Western, primarily American, and European institutions. What if scientists in other countries are more willing to consider unconventional hypotheses? What if Chinese or Russian or Indian researchers publish papers their Western counterparts won't? That would fragment the scientific discourse, creating parallel literatures that don't communicate well. We're already seeing hints of this with 3I-ATLAS, where some international groups seem more willing to discuss artificial origins than their American counterparts. The editor's ultimatum to Loeb crystallizes a tension that's been building in astrophysics for decades. As our observational capabilities improve, as we discover more exoplanets, and detect more interstellar objects and probe deeper into the cosmos, we're going to encounter things that don't fit neatly into our existing categories. Some will be natural phenomena we don't understand yet, but some might be artificial, products of technologies we can't imagine. How we respond to that ambiguity matters. If we approach it with the assumption that natural explanations must be right until proven otherwise beyond any doubt, we'll miss things. If we approach it with openness to evidence wherever it leads, we might discover something transformative. Loeb's refusal to quietly accept the editor's demand, his choice to make the censorship public and argue about it loudly in multiple forums, represents a bet on which approach will serve science better. Not everyone agrees with that bet. Some of his colleagues wish he'd been quieter, more diplomatic, more willing to work within the system rather than challenging it publicly. But the counter-argument is compelling. If the system is broken, if editorial gatekeeping is preventing legitimate investigation of important questions, then working within that system just perpetuates the problem. Sometimes you need to make noise, to force uncomfortable conversations, to risk looking foolish, because the alternative is never finding out if you're right. October 29th, Behind the Sun. October 29th, 2025, 7:47 AM Eastern Time. In the absolute silence of space, 130 million miles from Earth, 3I-ATLAS reaches perihelion, the closest point to the Sun in its hyperbolic trajectory through our solar system. The moment when solar irradiance peaks at 770 watts per square meter across its surface, enough energy to power a small city if you could somehow harness it. The moment when orbital velocity maxes out at 68 kilometers per second, faster than any human-made object has ever travelled. The moment when, if this thing is artificial, it would make its move, and we can't see any of it. Not from Earth anyway. 3I-ATLAS sits directly behind the Sun from our perspective, hidden in the solar glare, positioned exactly where ground-based telescopes are blind. The geometry is almost too perfect. Solar conjunction occurred 8 days earlier on October 20. First, placing the object on the opposite side of the Sun, perihelion happens while it's still hidden, while Earth-based observers are still waiting for it to emerge. If you were planning a trajectory that required doing something during perihelion without being watched by potential observers on Earth, you couldn't design better timing. That coincidence bothers Loeb more than almost anything else about 3I-ATLAS. He's calculated the probability. Take a random interstellar object entering the solar system from a random direction. What are the odds it would reach perihelion during solar conjunction as seen from Earth? The numbers depend on assumptions about the distribution of approach angles, but even generous calculations put it around 1%. Not impossible, but unusual. Add in all the other trajectory coincidence, the ecliptic alignment, the close approaches to multiple planets, and you're stacking unlikely events on top of each other. Each one alone is possible. Together they form a pattern that strains credulity. But here's the thing about patterns. Human brains are wired to find them even when they're not there, to see meaning in randomness, to detect agency where none exists. Pareidolia is the technical term, the tendency to perceive familiar patterns in random stimuli. We see faces in clouds, hidden messages in noise, conspiracies in coincidence. Scientists are trained to resist this, to demand statistical rigor before claiming a pattern is real rather than imagined. So when Loeb says the trajectory looks designed, when he points to the perihelion timing as suspicious, his critics counter that he's falling into the pareidolia trap. Of course, any specific trajectory will have some unlikely features if you look hard enough. That doesn't mean it's designed. Fair point. But there's a counter argument. Yes, we have to be careful about finding patterns in noise, but we also have to be careful about dismissing patterns in signal. If an artificial object were approaching the inner solar system, what would its trajectory look like? Probably something that maximized observation opportunities of major planets, while minimizing detection time. Probably something that took advantage of gravitational assists to adjust course efficiently. probably something that reached perihelion when it could do whatever it needed to do without immediate scrutiny. In other words, probably something that looked a lot like 3I-ATLAS. So how do we distinguish between a trajectory that happens to have design-like features and one that actually is designed? That's the fundamental epistemological challenge. In engineering, when you find something that looks designed, the null hypothesis is that it is designed unless you have evidence otherwise. In nature, the null hypothesis is that things are natural unless you have evidence otherwise. Those opposite defaults make sense in their respective domains. But what do you do with something from interstellar space where you don't know which domain applies? Loeb's answer is that you gather evidence without prejudice. You observe as thoroughly as possible, you measure everything measurable, and you evaluate all hypotheses, natural and artificial, based on how well they fit the data. The problem is that gathering evidence requires access, and access during perihelion required spacecraft positioned away from Earth. Which brings us back to those missing high-rise images from October 2nd and 3rd, the last clear observations before 3I-ATLAS disappeared behind the Sun. But it's not quite true that we couldn't see anything during perihelion. Space-based solar observatories had angles that Earth didn't. The Solar and Heliospheric Observatory, SOHO, orbiting at the L1 Lagrange point between Earth and Sun, had instruments that could potentially detect 3I-ATLAS against the solar background. The Parker Solar Probe, deep in the inner solar system pursuing its mission to study the Sun up close, might have caught something. The Solar Orbiter, ESA's mission in an elliptical path around the Sun, could have had line of sight. These spacecraft weren't designed to observe comets. Their instruments are optimized for solar science, studying the corona and solar wind and magnetic fields. But if something unusual happened during perihelion, something bright enough or energetic enough or otherwise anomalous, these missions might have detected it as a side effect. Did they? We don't know. Data from Parker Solar Probe and Solar Orbiter goes through NASA and ESA respectively, and as we've established, both agencies have been remarkably quiet about their 3I-ATLAS observations. SOHO data is more accessible, some of it appears in near real time for space weather monitoring, but searching through SOHO images for a faint comet during solar conjunction requires expertise and time. Amateur astronomers have tried, examining publicly available SOHO coronagraph images from late October. Some claim to have spotted 3I-ATLAS. Others say the claimed detections are artifacts or background stars. Without official confirmation, it's hard to know what to believe. What we do know is that 3I-ATLAS survived perihelion. It didn't fragment under solar heating, didn't break apart into smaller pieces the way some comets do when thermal stress exceeds their structural strength. We know this because observations in early November, once the object emerged from solar conjunction, showed a single coherent nucleus with expected brightness. That's actually somewhat surprising. The thermal load at perihelion was immense, enough to vaporize significant amounts of ice if the nucleus is mostly cometary. For 3I-ATLAS to come through intact suggests either it's more robust than typical comets, or it's made of something more refractory than ice. Early November observations also revealed something else interesting. 3I-ATLAS appeared brighter than predicted, and bluer. The brightness increase makes sense. Comets often outgas more as they approach perihelion, creating larger comas that reflect more sunlight. But the colour shift is unusual. Before perihelion, spectroscopic observations showed 3I-ATLAS was relatively red, consistent with organic compounds called tholins coating the surface. After perihelion, it appeared significantly bluer in some wavelength bands. That suggests the composition of the coma changed, either because different volatiles sublimated at perihelion temperatures, or because something else happened to alter the dust and gas mixture surrounding the nucleus. Loeb has a hypothesis about that colour shift, though he's careful to label it as speculative. If 3I-ATLAS released smaller objects during perihelion, mini probes in his terminology, those objects would initially travel very close to the parent body before solar radiation and gravitational effects separated their paths. The combined light from the nucleus plus probes might show a different colour than the nucleus alone, especially if the probes were made of different materials. As the weeks pass and the probes move away from the main body, the colour would shift back toward what we expect from the nucleus. This is testable. If probes were released, we should eventually detect them as separate objects once they're far enough from the nucleus to be resolved individually. That's why the December 19th closest approach to Earth matters so much. At 1.8 astronomical units, 3I-ATLAS will be close enough that large telescopes can potentially resolve structure. If there are multiple objects travelling in formation, if something separated from the main nucleus during perihelion, we should be able to see it. Hubble can resolve features about 10 kilometers across at that distance. Ground-based telescopes with adaptive optics can do even better under good conditions, and not just imaging. Spectroscopy can detect multiple velocity components if several objects are moving together. The December observations will either show a single nucleus or reveal something more complex. But let's talk about what else perihelion represents in the context of spacecraft operations. It's not just the closest approach to the Sun, it's the point of maximum kinetic energy, which means it's the optimal place to execute maneuvers if you want to maximize the effect of thrust. This is called the Oberth effect, named after Hermann Oberth, who first described it mathematically. The basic principle is simple. If you burn rocket fuel when you're already moving fast, you get more energy change than if you burn the same fuel when you're moving slowly. The reason involves orbital mechanics and energy equations, but the upshot is that perihelion is special for any spacecraft that needs to change velocity. Now, if 3I-ATLAS is just a comet, the Oberth effect is irrelevant. Comets don't have engines. They don't plan. Maneuvers. But if it's artificial, if it's some kind of probe or explorer from another civilization, then reaching perihelion while hidden from Earth makes perfect sense. You'd wait until you're moving fastest, when fuel efficiency is maximum, to execute whatever trajectory changes you need. Maybe you want to decelerate so you can enter orbit around one of the inner planets. Maybe you want to release smaller vehicles that can visit multiple destinations. Maybe you want to adjust your exit trajectory for some reason. Whatever the goal, perihelion is when you'd act. And the object did show non-gravitational acceleration. Data from the Atacama Large Millimeter Array in Chile, analysed after perihelion, indicated 3I-ATLAS was about 4 arcseconds away from where it should have been based on purely gravitational calculations. 4 arcseconds might not sound like much, but at the distance involved it translates to significant displacement. Something pushed 3I-ATLAS off its predicted path. The question is what? Comets routinely show non-gravitational acceleration. It's called the rocket effect, or sometimes the jet effect. When ice sublimates on one side of the nucleus, the escaping gas provides a tiny thrust. It's usually small but measurable, and it means cometary trajectories deviate slightly from what you'd predict using gravity alone. So non-gravitational acceleration doesn't automatically mean artificial propulsion. It might just mean 3I-ATLAS is outgassing asymmetrically, which would be completely normal for a comet. But the magnitude matters. Loeb calculated that the observed acceleration, about 0.02 millimeters per second squared, would require 3I-ATLAS to lose roughly 1/6 of its total mass. That's a lot. More than you'd typically expect even for a very active comet during perihelion. If 3I-ATLAS really did shed that much mass, we should see evidence in 2 ways. First, the coma should be enormous, containing billions of tons of gas and dust. Second, the nucleus should be noticeably smaller or fainter in December observations compared to earlier images. If we don't see those effects, if the gas cloud is too small and the nucleus hasn't shrunk, then cometary outgassing doesn't explain the acceleration, which leaves the artificial propulsion hypothesis looking more plausible. This is why the December observations are so crucial. They're not just about finding mini probes or detecting structure. They're about testing whether the non-gravitational acceleration can be explained naturally or requires something else. And that's a question we can answer with data rather than speculation. Measure the size of the gas cloud. Compare the nucleus brightness before and after perihelion. Check whether the mass loss implied by the acceleration matches what we observe. If it does, natural explanation prevails. If it doesn't, we have a problem that needs explaining. There's another test that could have been performed during perihelion but wasn't, or at least wasn't made public. Radio observations. If 3I-ATLAS is artificial, if it's communicating with whoever sent it, or with smaller probes it might have released, it would likely use radio frequencies. The solar system is full of radio noise, but structured signals would stand out against that background. SETI researchers know how to look for this kind of thing. They've been doing it for decades, pointed at distant stars. Turning those techniques toward 3I-ATLAS during perihelion would have been straightforward. Did anyone do it? Loeb tried to organize radio observations through the Galileo project, but telescope availability during the critical window was limited. Some amateur radio astronomers claimed to point antennas at the object, but detecting signals would require sophisticated signal processing, and it's unclear if anything was found. Official observatories with the sensitivity to detect weak signals didn't announce any campaigns, or if they did observe, they haven't released results. This is frustrating because radio observations are one of the clearest ways to test the artificial hypothesis. Natural objects don't produce structured radio signals. Finding any would be definitive. The lack of public radio observations during perihelion might just be bad timing and coordination, but it might also reflect the stigma around looking for evidence of artificial origins. No astronomer wants to be the one who pointed a radio telescope at 3I-ATLAS and found nothing, then have that null result used to mock the search as a waste of resources. The career risk isn't symmetric. If you look and find something, you're a hero. If you look and find nothing, you're the fool who took alien hypotheses seriously. That asymmetry discourages searches, which means we might miss real signals because scientists are afraid of looking foolish. Perihelion also represented a moment of vulnerability for 3I-ATLAS if it's natural. The heating was intense enough to potentially cause structural failure if the nucleus wasn't solid enough. Some comets do break apart during perihelion, unable to withstand thermal stress. The fact that 3I-ATLAS didn't fragment tells us something about its composition or internal structure. It's either made of stronger stuff than typical comets, or it's held together by something more robust than the weak gravity and van der Waals forces that bind cometary nuclei. You could imagine natural explanations. Maybe 3I-ATLAS formed in a particularly cold region of its home system, accreting at temperatures where harder ices like carbon monoxide or nitrogen dominate over water ice. Maybe it spent billions of years in interstellar space getting irradiated by cosmic rays, which can chemically alter surface materials and create more refractory crusts. Maybe it's just unusually large, and larger objects have stronger self-gravity that helps hold them together, all plausible. But also, if you're building an interstellar probe, you'd design it to survive perihelion heating. You'd use materials that can withstand high temperatures without structural failure. The real frustration of October 29th is that it was the test, the moment when artificial and natural predictions diverged most sharply, and we couldn't watch it happen. If 3I-ATLAS manoeuvred, if it released probes, if it transmitted signals, if it did anything that comets don't do, perihelion was when it would happen. And that window occurred while the object was perfectly positioned where Earth couldn't observe it. We're left picking through indirect evidence, trying to reconstruct what happened from observations before and after, without direct data from the critical moment. Was the timing coincidental or designed? That's the question that keeps circling back, and maybe we'll never know for sure because the evidence that would answer it definitively, real-time observations during perihelion, doesn't exist or isn't being shared. What we do know is that 3I-ATLAS survived, emerged from conjunction slightly off its predicted path, appeared brighter and bluer than expected, and showed no signs of fragmentation despite intense heating. What those facts mean depends on interpretation, and interpretation depends on what assumptions you start with about what's plausible. In a few weeks, when December 19th arrives and 3I-ATLAS makes its closest approach to Earth, we'll get better data. Higher resolution images, more detailed spectroscopy, precise position measurements that will clarify the non-gravitational acceleration. Maybe that data will resolve the ambiguities, answer the questions that perihelion left hanging. Or maybe it will just deepen the mystery, revealing more anomalies that don't quite fit either the comet model or the artificial probe model. Either way, October 29th will be remembered as the moment we couldn't watch, the day when something potentially significant happened behind the sun, and humanity waited in frustration for answers that would only come later, if they came at all. The trajectory anomaly. The Atacama Large Millimeter Array sits high in the Chilean Andes, 66 radio telescopes working together as a single instrument to observe the universe at millimeter and submillimeter wavelengths. It's one of the most powerful astronomical facilities on Earth, capable of detecting faint signals from the most distant galaxies or tracking the subtle movements of objects much closer to home. On October 29th, while 3I-ATLAS reached perihelion hidden from most observers, ALMA was watching. The observatory's position in the southern hemisphere and its ability to observe in wavelengths less affected by solar glare gave it an angle that many other facilities lacked. The data ALMA collected wouldn't be processed and released immediately. These observations require careful calibration, extensive computational analysis, verification against multiple references. But by early November, as results filtered through the usual channels of scientific communication, something unusual emerged. 3I-ATLAS wasn't quite where it should have been. The deviation was small, measured in arcseconds, but at interstellar distances small angular errors translate to enormous spatial displacements. 4 arcseconds. That's what the preliminary ALMA data showed. 4 arcseconds away from the position predicted by gravitational calculations. 4 arcseconds is about 1/450th the angular diameter of the full moon. Tiny by human perception standards. But for an object 2 astronomical units from Earth, 4 arcseconds means roughly 1.1 million kilometers of lateral displacement, nearly 3 times the distance from Earth to the moon. Something had pushed 3I-ATLAS off course, and pushed it hard enough to be detectable across interstellar space. Now, as established earlier, non-gravitational acceleration in comets is common. The rocket effect from asymmetric outgassing accounts for small trajectory deviations all the time. What makes the ALMA measurement significant is the magnitude. 4 arcseconds is large for cometary acceleration, though not impossible. The question becomes whether the mass loss required to produce that much acceleration matches what we observe in the coma surrounding 3I-ATLAS. And that's where things get interesting. Loeb ran the numbers immediately when he saw the ALMA results. Using basic momentum conservation, you can calculate how much mass a comet needs to eject to produce a given acceleration. The equation involves the ejection velocity of sublimated gas, typically a few hundred meters per second for water ice, and the observed acceleration, 0.02 millimeters per second squared from the ALMA data. When you work through the math, you find that 3I-ATLAS would need to lose about 1/6 of its total mass over the course of a month to account for that acceleration. 1/6. Think about that for a moment. If 3I-ATLAS has a mass around 33 billion tons, which is what earlier analysis suggested based on the lack of strong acceleration from solar radiation pressure, then 1/6 means about 5.5 billion tons of material ejected. That's not outgassing. That's explosive mass loss, the kind of thing you'd see from a comet breaking apart or undergoing some catastrophic event, except 3I-ATLAS didn't break apart. Post-perihelion observations show a single intact nucleus, not fragments dispersing into space, so we have a puzzle. The trajectory says massive mass loss. The images say no breakup. How do you reconcile those? One possibility is that the mass estimates are wrong. Maybe 3I-ATLAS is much less massive than calculated, which would mean less mass loss is needed to produce the observed acceleration. But lower, mass creates other problems. If the object is too light, solar radiation pressure should have pushed it off course much more dramatically than we observe. There's a balance point where the mass is large enough to resist radiation pressure, but small enough that cometary outgassing can produce the measured acceleration, and that balance point is narrow. Threading that needle requires very specific assumptions about composition and structure. Another possibility is that the outgassing is extremely efficient, producing more thrust per unit mass than typical cometary jets. This could happen if the volatile ices are particularly energetic, like carbon monoxide, which sublimes at lower temperatures than water and has higher molecular velocity. Or maybe the geometry of the nucleus creates focused jets that direct thrust more effectively than the diffuse outgassing most comets show. Both scenarios are plausible, but both are also convenient explanations for an observation that doesn't quite fit the standard model. A third possibility, the one Loeb keeps returning to, is that the acceleration isn't from outgassing at all. If 3I-ATLAS has some kind of propulsion system, even a relatively weak one by spacecraft standards, it could produce the observed acceleration without requiring massive mass loss. The energy budget matters here. At perihelion, 3I-ATLAS receives over 33 gigawatts of solar power hitting its surface. That's an enormous energy source if you have any way to harness it. Solar sails work by reflecting photons, getting momentum transfer without expending fuel. More sophisticated systems might convert solar energy to electricity and use that to power ion drives or other high-efficiency propulsion. You wouldn't get dramatic acceleration from these systems, but you'd get exactly the kind of small sustained acceleration that ALMA measured. The timing of the acceleration is also suggestive. It appears to have peaked around perihelion, exactly when solar energy input was maximum, and exactly when the Oberth effect would make any maneuver most efficient. If you're a comet, perihelion is when you outgas most because heating is most intense. If you're a solar-powered spacecraft, Perihelion is when you have most power available, and when thrust is most effective. Both predictions point to the same timing, which makes perihelion observations critical, but also ambiguous. Seeing increased activity at perihelion doesn't tell you which explanation is correct. But here's where it gets more complicated. The ALMA measurement shows acceleration, but acceleration in which direction? That matters because different directions imply different causes. If the acceleration is radial, pointing directly away from the Sun, that's most consistent with solar radiation pressure or symmetric outgassing. If it's tangential, in the direction of orbital motion or against it, that suggests asymmetric jets or deliberate propulsion. If it's out of plane, perpendicular to the orbit, that's harder to explain naturally and might indicate manoeuvring. The preliminary ALMA data doesn't clearly resolve the direction, or at least the publicly released summaries don't specify it with enough precision to distinguish these cases. This is frustrating because directional information would significantly constrain the explanation. A targeted measurement campaign with multiple observatories could pin down the acceleration vector precisely, separating radial, tangential, and perpendicular components. But that requires coordination and resources that haven't been marshalled, possibly because most astronomers still assume the natural explanation is correct and don't see the need for intensive follow-up. There's also a question about whether the acceleration is constant or variable. If it's steady over time, that suggests a persistent cause like a continuously firing engine or ongoing asymmetric outgassing. If it varies, spiking at certain times and dropping at others, that might indicate periodic jets tied to the rotation of the nucleus or intermittent engine burns. ALMA caught one snapshot at perihelion, but tracking 3I-ATLAS over weeks or months would reveal the temporal behaviour. That data might exist in telescopes' archives, waiting for someone to analyse it, or it might not exist because continuous monitoring wasn't prioritised. Independent amateur astronomers have tried to measure the position of 3I-ATLAS using their own equipment, comparing it to the JPL Horizons predictions to see if the ALMA anomaly shows up in other datasets. Some claim to have confirmed the discrepancy, reporting measurements that agree with ALMA to within their error bars. Others find no significant deviation, though their measurements are typically less precise. Reconciling these different results requires careful error analysis and understanding of systematic effects, work that hasn't been done comprehensively yet, or at least hasn't been published. What makes this particularly tantalizing is that the trajectory anomaly was predicted, not by conventional cometry models, but by the artificial probe hypothesis. If 3I-ATLAS were executing an Oberth maneuver at perihelion, exactly this kind of position discrepancy would show up in post-perihelion observations. The object would emerge from solar conjunction, slightly off the predicted gravitational trajectory, having used the Sun's gravity well to boost the efficiency of whatever thrust it applied. The fact that ALMA measured exactly such a deviation, at exactly the expected time, makes the coincidence troubling. Of course, you can't claim prediction after the fact and use it as strong evidence. That's the difference between prediction and postdiction. A genuine test of a hypothesis requires predicting something before you observe it, then checking if reality matches. But Loeb did publish the Oberth maneuver possibility before perihelion, arguing that October 29th was the critical date to watch, so when ALMA data showed trajectory anomalies emerging right around that date, it at least weakly supports his hypothesis in a way that pure postdiction wouldn't. The counter-argument is that any sufficiently flexible hypothesis can accommodate observations after the fact. If perihelion had come and gone with no measurable trajectory changes, proponents of the artificial hypothesis could have said, well, maybe it didn't need to maneuver this time, or maybe the maneuver was too small to detect, or maybe we were wrong about the timing. Hypotheses that can explain any outcome don't constrain reality usefully. The artificial probe hypothesis needs to make specific falsifiable predictions that could prove it wrong. Does the trajectory anomaly constitute such a prediction? Partially. If no anomaly had been detected, that would have been evidence against artificial origins. The fact that an anomaly was detected is consistent with artificial origins, but also consistent with active cometry behaviour, so it's weak evidence at best. What would constitute strong evidence? Several things. First, if the trajectory anomaly grows over time in ways that can't be explained by outgassing. If 3I-ATLAS continues to accelerate in controlled ways through November and December, executing multiple burns or trajectory corrections, that would be very hard to explain naturally. Second, if the gas cloud around 3I-ATLAS turns out to be too small to account for the observed acceleration, that's the test Loeb keeps emphasizing. If we're supposed to believe 5 billion tons of material was ejected, we should see 5 billion tons of material in the coma and tail. If we don't, the natural explanation fails. Third, if multiple objects are detected travelling in formation, separated from the main nucleus in ways that suggest intelligent deployment rather than random fragmentation. All of these tests are achievable with December observations. Large telescopes imaging 3I-ATLAS at closest approach can measure whether the nucleus has shrunk, whether the gas cloud is as massive as theory predicts, whether multiple objects are present. Spectroscopy can determine composition and mass loss rates. Radar observations, if anyone conducts them, can probe internal structure and detect rotation changes that might indicate mass redistribution. The data needed to resolve these questions is obtainable. Whether it will be obtained and analysed comprehensively depends on funding, telescope allocation, and scientific priorities that aren't always driven by the most interesting questions. There's a sociological dimension to this worth acknowledging. Most astronomers believe 3I-ATLAS is a comet, full stop. That belief is reasonable given base rates. Most objects are natural, and shapes their research priorities. They'll observe 3I-ATLAS as time and resources allow, but they're not dropping everything to mount intensive campaigns because they expect the results to show normal cometary behaviour. If you genuinely think the artificial hypothesis is plausible, you design observation programs very differently, targeting specific tests that could distinguish artificial from natural with high confidence. But designing those programs requires convincing telescope allocation committees, peer reviewers, and funding agencies that the tests are worth doing. And that's hard when the mainstream consensus is that the question is already answered. Loeb has tried to organise coordinated observation campaigns through the Galileo project, but even with his visibility and resources, getting telescope time is challenging. Every astronomer wants to use major facilities. Telescope schedules are booked months in advance with carefully reviewed proposals. Getting emergency time for target of opportunity observations is possible, but requires convincing directors that your target justifies bumping approved programs. 3I-ATLAS is interesting, sure, but is it more interesting than distant supernovae or exoplanet transits or galaxy surveys that have been planned for years? Different people will answer that differently depending on their priors about how likely artificial origins are. The trajectory anomaly sits in an uncomfortable middle ground. It's significant enough that dismissing it entirely feels premature, but it's not dramatic enough that it forces consensus about the need for intensive follow-up. If 3I-ATLAS had deviated by degrees rather than arc-seconds, if the acceleration were orders of magnitude larger, everyone would agree something extraordinary was happening. If there were no detectable deviation at all, the natural explanation would be confirmed and we could move on. But 4 arc-seconds is just ambiguous enough to support multiple interpretations without strongly favouring any of them. It's the kind of observation that should trigger careful investigation, but in practice often gets noted and then left for someone else to follow up on. Amateur astronomers and independent researchers are trying to fill that gap, monitoring 3I-ATLAS with whatever equipment they can access, sharing data online, analysing images that professional observatories haven't gotten around to looking at yet. This democratization of astronomy is powerful, letting distributed networks of observers contribute to science in ways that were impossible a generation ago. But it's also messy. Amateur data has larger error bars, more systematic effects, less rigorous calibration. Separating real signals from artifacts requires expertise that not all contributors have. So you get claims and counterclaims, some amateur observers reporting anomalies while others find nothing unusual, and without professional verification it's hard to know what's reliable. What's needed is a comprehensive, well-funded, professionally conducted observation campaign treating 3I-ATLAS as a high priority, target and marshalling the resources to characterise it thoroughly. That's not happening, at least not publicly, which means we're relying on piecemeal observations fitted around other priorities. And that might be adequate if 3I-ATLAS is just an unusual comet. But if it's something more, if the trajectory anomaly signals actual propulsion or manoeuvring, we might be missing a chance to gather definitive evidence simply because we couldn't organise the scientific response quickly enough. History might look back on this moment and wonder why we didn't take the possibility more seriously. why we let an interstellar visitor pass through our system without mounting the kind of intensive study its anomalies warranted. Or history might look back and say reasonable scientists reasonably concluded it was probably natural and reasonably prioritized accordingly, and they were right. Time will tell which interpretation prevails. Mini-probes and mothership theory. Imagine you're an engineer tasked with designing an interstellar reconnaissance mission. Not science fiction, but a real engineering problem with real constraints. Your goal is to study a planetary system 50 light-years away. You have technology that can accelerate a probe to some fraction of light speed, let's say 10% to be generous. That means 500 years travel time. Your probe needs to function after centuries in the harsh environment of interstellar space. It needs to decelerate when it arrives, study multiple planets in the target system, and probably send information back home. How do you design it? The first problem is mass. Every kilogram you accelerate to 10% of light speed requires enormous energy. Bigger probes need more fuel for deceleration, which makes them heavier, which requires more energy to accelerate. It's a vicious cycle. The solution is to keep the main vessel as small as possible while still accomplishing the mission. But if you want to study multiple planets, particularly ones at different orbital distances from the star, sending a single probe to each one requires that single probe to maneuver extensively, burning fuel and time. There's a better approach. Send a mothership, relatively large and robust, that doesn't need to maneuver much. Have it follow a trajectory that passes through the inner system, coming reasonably close to multiple planets without needing powered flight to reach each one. Then, at optimal points along that trajectory, release smaller vehicles, mini-probes that can execute their own maneuvers to intercept specific targets. The mothership continues on its main path, maybe exiting the system or entering a long elliptical orbit for continued observation. The mini-probes scatter to their destinations, each one specialized for its particular target. This isn't speculative. It's how we design missions in our own solar system. The Voyager spacecraft didn't stop at each planet it visited. It flew by on a carefully calculated trajectory that natural gravity shaped. Modern mission concepts for exploring the outer solar system talk about motherships that release multiple smaller probes rather than sending individual spacecraft to each moon of Jupiter or Saturn. It's more efficient. It provides redundancy. It maximizes science return for the energy invested in getting there. If 3I-ATLAS is artificial, if it represents an interstellar mission designed by a civilization with similar engineering constraints to ours, albeit more advanced technology, the mothership plus mini-probes architecture makes sense. And the trajectory 3I-ATLAS follows, the one that bothered Loeb from the beginning, fits this architecture almost perfectly. Close approach to Mars, perfect for releasing a probe toward the inner rocky planets. Perihelion near Earth's orbit, ideal for deploying vehicles toward Venus or Earth. Later pass by Jupiter, allowing observation or probe release toward the outer system. The whole trajectory reads like a mission profile designed to maximize planetary encounters with minimum fuel expenditure. The question then becomes, when would such a mission release its mini-probes? And the answer, both from orbital mechanics and from operational security, is perihelion. The Oberth effect gives you maximum efficiency when you're moving fastest and closest to the central star. Any velocity change you impart to a probe at perihelion gets amplified by the gravitational environment. A small thrust becomes a large trajectory change. And perihelion for 3I-ATLAS occurred when the object was hidden from Earth observation, which, if you're trying to avoid detection by the local inhabitants, is exactly when you'd want to do something unusual. Loeb has worked through the orbital mechanics in detail. A mini-probe released from 3I-ATLAS at perihelion with a modest velocity kit could reach Earth orbit within months. The numbers depend on how much delta-v the probe can generate, but with velocities of a few kilometers per second, well within what our own chemical rockets achieve, an Earth intercept by early 2026 is feasible. The probe wouldn't need much fuel. It's not fighting against gravity, it's using solar gravity to help curve the trajectory. The mothership does most of the work getting into the system. The probe just needs to adjust from the mothership's path to an Earth intercept trajectory. Similar calculations apply to Mars, Venus, or any of the other destinations you might want to study. The fact that 3I-ATLAS passed relatively close to Mars before perihelion means a probe released during that encounter could have entered Mars orbit, or impacted the surface with even less delta-v required. Did that happen? We have no evidence of it, but we also wouldn't necessarily detect a small probe in Mars orbit unless we were looking for it. Our inventory of artificial satellites around Mars tracks things we put there. An unknown object, especially, a small one, might escape notice unless it did something to call attention to itself. The geometry of Earth observations matters here. From our perspective, anything released from 3I-ATLAS during perihelion would initially appear very close to the nucleus. It might take weeks or even months for the objects to separate enough that we could resolve them as distinct entities rather than a single fuzzy blob. This is where December 19th becomes critical. At closest approach to Earth, telescopes will have their best shot at detecting structure, at seeing whether 3I-ATLAS is one object or multiple objects travelling in loose formation. What would mini-probes look like if we detected them? That depends entirely on their design and purpose. If they're passive, just observing and recording without active systems, they'd be very hard to spot. You'd need reflected sunlight to see them, and smaller objects reflect less light. Something a few meters across might be detectable with large telescopes if you knew where to look, but searching the space around 3I-ATLAS for unknown small objects is challenging. If they're active, broadcasting radio signals or using active sensors, we might detect their emissions. If they're maneuvering with visible exhaust or changing reflectivity, we might notice the variability. There's also the possibility that we've already detected mini-probes without recognizing them. The optical and radar systems that track satellites and space debris around Earth are optimized for known object types moving in predictable orbits. An object on an interplanetary trajectory approaching from an unusual angle might register as a spurious detection or get classified as measurement error. Unless someone specifically looks through the archives checking for objects whose trajectories trace back to 3I-ATLAS around perihelion, we might miss them. Loeb has actually tasked the Galileo Project observatories with exactly this kind of monitoring. The project operates 3 dedicated telescopes in Massachusetts, Pennsylvania and Nevada, designed to detect and characterize anomalous aerial phenomena. In the context of 3I-ATLAS, that means watching for objects near Earth that show motion patterns inconsistent with natural meteors or artificial satellites. If mini-probes were released and are approaching Earth, Galileo instruments might spot them. Whether they'd recognize what they're seeing is another question. Distinguishing a true anomaly from the myriad false positives that plague sky surveys requires careful analysis and usually multiple confirming observations. The mothership theory makes specific predictions that are testable. First, if 3I-ATLAS released probes, its mass should have decreased by an amount equal to the probe's total mass. That's conservation of mass, basic physics. If we can measure the nucleus size precisely in December and compare it to earlier measurements, we can check whether it shrank. Second, the trajectory should show momentum transfer. Releasing probes isn't passive. The mothership would recoil, changing its trajectory slightly depending on what direction the probes were ejected. That recoil is measurable if it's large enough, and if we have precise position data. Third, the probes themselves should eventually be detectable as separate objects once they've moved far enough from the nucleus. None of these predictions have been definitively tested yet because we're still waiting for the December close approach that will provide the resolution needed. But they're concrete enough that when December observations happen, we'll be able to say with some confidence whether they support or refute the mothership hypothesis. If the nucleus hasn't shrunk, if the trajectory shows no recoil effects, if no separate objects are detected, then the mini-probe scenario looks much less likely. If all 3 signatures appear, then we have to take the hypothesis seriously regardless of how improbable it seemed initially. There's a variant of the mothership theory worth considering. Maybe 3I-ATLAS isn't releasing probes now. Maybe it did so weeks or months ago, possibly during the Mars approach or even earlier. Those probes could already be dispersed throughout the inner solar system, quietly observing from positions we haven't checked. This version is harder to test because it doesn't predict anything specific about December observations. But it does suggest we should be looking more broadly, not just at 3I-ATLAS itself, but at the space around Earth for objects that shouldn't be there. Radio observation of 3I-ATLAS could also test the mothership theory. If the object is coordinating with released probes, it might communicate with them using radio. The signals wouldn't necessarily be directed at Earth. We might just catch spillover from transmissions aimed at the probes, but any structured radio emission would be significant. Natural comets don't produce coherent radio signals. Some produce radio noise from ionized gas or plasma interactions, but that's broad spectrum and incoherent, very different from what a communication system would generate. dedicated radio telescope time on 3I-ATLAS during December could search for signals. Whether such observations are planned depends on whether anyone with telescope access takes the possibility seriously enough to use limited resources looking for it. The skeptical response to all this is that we're building elaborate scenarios on a foundation of ambiguous evidence. Yes, 3I-ATLAS has unusual features. Yes, its trajectory is rare. Yes, the perihelion timing is suspicious. But unusual doesn't mean artificial. Rare doesn't mean designed. Suspicious doesn't mean proof. Every claim of alien technology in the past has turned out to be natural phenomena we didn't understand yet. Pulsars were briefly thought to be alien beacons until we figured out they're rotating. Neutron stars. Radio signals from Jupiter seemed artificial until we understood planetary magnetospheres. The track record of extraordinary claims about extraterrestrial intelligence is abysmal. Why should 3I-ATLAS be different? That's a fair point, and Loeb doesn't really dispute it. His argument isn't that 3I-ATLAS is definitely artificial. It's that the hypothesis shouldn't be dismissed without proper investigation. And proper investigation means treating artificial origins as a testable scientific question rather than a fringe speculation. Design specific observation campaigns to look for evidence that would distinguish artificial from natural. Use the best instruments we have to characterize the object thoroughly. And if all the tests come back negative, if every prediction of the artificial hypothesis fails, while natural explanations succeed, then we can confidently conclude it's natural and move on. But skipping the test because we assume we already know the answer isn't science, it's prejudice. The mini-probe hypothesis is particularly useful because it makes the artificial origins question concrete. Instead of vague speculation about whether advanced aliens might visit us, we have a specific scenario with specific predictions. Probes should be detectable if they exist. They should produce observational signatures that differ from cometary behaviour. The mothership should show mass loss and recoil. These are things we can measure, not philosophical questions about the nature of intelligence or the likelihood of interstellar travel. Turn telescopes, run the observations, analyse the data, see what it shows. If the December observations reveal mini-probes, if we actually detect multiple objects where we expected one, the implications are staggering. It wouldn't just confirm that we're not alone. It would mean alien technology is in our solar system right now, potentially observing us, possibly landing on Earth or other planets. The entire framework for thinking about humanity's place in the universe would shift overnight. Every institution, from governments to religions, would need to reckon with that reality. It would be, without exaggeration, the most important discovery in human history. But if December comes and goes with nothing unusual detected, if 3I-ATLAS looks in every way like a strange but natural comet, does that disprove the artificial hypothesis? Not entirely, but it weakens it substantially. You could always argue the probes are too small to see, or that they were released but aren't coming to Earth, or that the technology is advanced enough to avoid detection. But at some point, if none of your predictions pan out, you have to accept that the hypothesis isn't useful. Science works by testing ideas and discarding the ones that don't match reality. The artificial origins hypothesis has had its tests proposed. December will show whether it passes them. And maybe, just maybe, there's a middle ground that's been overlooked in all this. What if 3I-ATLAS is natural but unusual enough that it's teaching us something genuinely new about comets or interstellar objects? What if the anomalies we're seeing reflect physics or chemistry we don't fully understand rather than artificial construction? That would still be valuable. That would still advance knowledge. The danger in focusing too much on the artificial versus natural dichotomy is that we might miss the real scientific story, which is that 3I-ATLAS doesn't fit neatly into our existing categories and is forcing us to expand them. Whether that expansion includes alien technology or just exotic astrophysics, either way we learn something important. And isn't that what science is supposed to be about? Learning new things rather than confirming what we already believe we know? The Nickel Signature Controversy, August 24th, 2025. The Keck 2 telescope in Hawaii, one of the most powerful optical instruments on Earth, points toward 3I-ATLAS. The target is still distant, more than 2.5 astronomical units from both the Sun and Earth. But Keck's 10-meter mirror and sophisticated spectrographs can tease out details invisible to smaller telescopes. The Keck Cosmic Web Imager captures light across a broad wavelength range, from deep ultraviolet through visible into the red. Then the data gets processed, turned into spectra showing which wavelengths are bright and which are dim, revealing the chemical fingerprint of gases surrounding the nucleus. The results are puzzling. Strong emission lines from nickel dominate the spectrum. Nickel, element 28 on the periodic table, a silvery metal that shouldn't be abundant in cometary gas. But even more puzzling is what's missing: iron. Element 26, nickel's close neighbour in the periodic table, and its constant companion in cosmic chemistry. In every natural setting we know, nickel and iron occur together in roughly predictable ratios. Meteorites contain both. Planetary cores are iron-nickel alloys. Stellar atmospheres show iron and nickel in proportions that reflect how those elements are synthesized in supernovae. But 3I-ATLAS shows nickel without corresponding iron. The ratio is off by orders of magnitude compared to any natural object ever observed. This isn't the first time astronomers have detected nickel in comets. The element appears occasionally in cometary spectra, usually in tiny amounts, part of the trace metal content you'd expect from materials that formed in the early solar system. What makes 3I-ATLAS different is the abundance and the ratio. This isn't trace contamination. This is a dominant component of the coma, and it's essentially pure nickel without the iron you'd expect to accompany it. The paper analysing the Keck data, published in October, tries to explain this anomaly through a natural process. The authors propose that nickel tetracarbonyl forms near the nucleus through chemical reactions between nickel atoms and carbon monoxide. Nickel tetracarbonyl is a strange molecule. 4 carbon monoxide molecules bonded to a single nickel atom. It's volatile, vaporizing at relatively low temperatures, which could explain why nickel appears in the coma even when 3I-ATLAS is far from the Sun. The molecule is also highly selective for nickel over iron under certain conditions, which might explain the skewed ratio. This is actually a reasonable hypothesis. Nickel tetracarbonyl is real. It's used industrially in the Mond process for refining pure nickel from ore. The chemistry works. Under the right temperature and pressure conditions, you can preferentially extract nickel while leaving iron behind. The question is whether those conditions exist naturally in cometary environments. On Earth, the Mond process requires careful control of temperature and carbon monoxide pressure. Does 3I-ATLAS somehow provide those conditions spontaneously? The paper argues yes, suggesting that local conditions near the nucleus allow nickel tetracarbonyl formation in situ. They predict the nickel should be concentrated close to the nucleus, within a few hundred kilometers, which the Keck images seem to confirm. Beyond that radius, the molecule breaks down, and nickel atoms disperse into the broader coma. The spatial distribution matches what you'd expect if this chemistry is happening, so maybe the natural explanation works after all. But Loeb isn't convinced, and his skepticism is based on more than just contrarian instinct. The industrial nickel refining process isn't something that happens by accident. It requires specific conditions that metallurgists spent decades figuring out how to achieve reliably. The temperatures need to be warm enough for the reaction to proceed, but cool enough that the nickel tetracarbonyl doesn't immediately decompose. The carbon monoxide pressure needs to be high enough for the molecules to collide frequently, but not so high that other reactions dominate. Getting all these conditions right simultaneously is tricky. That it would happen naturally in a comet, producing enough nickel emission to dominate the spectrum, strains credulity. There's also the question of where the nickel comes from in the first place. Comets are made mostly of ice, water ice, carbon dioxide ice, maybe some ammonia and methane. The solid fraction is mostly silicate dust with trace amounts of metals. Nickel is present but typically in very small concentrations, parts per million at most. To produce the observed nickel emission, you need either very efficient extraction of nickel from the dust, releasing nearly every nickel atom into the coma, or you need the nucleus to be enriched in nickel compared to typical cometary material. Neither scenario is impossible, but both require special conditions. Enrichment could occur if 3I-ATLAS formed in a region of its home system where nickel was unusually abundant. Maybe near a supernova remnant where freshly synthesized nickel hadn't mixed thoroughly with the interstellar medium. Maybe in the debris from a planetary collision that excavated core material rich in metals. These scenarios are speculative but not crazy. The universe is large and diverse, and the conditions that prevailed when 3I-ATLAS formed billions of years ago might have been very different from what we see in our solar system today. But here's where the artificial hypothesis offers a simpler explanation. If you're building an interstellar probe, you need materials that can withstand centuries in space, survive passage through the interstellar medium, and remain functional after exposure to cosmic rays and micrometeoroids. You need structural strength, thermal stability, and resistance to corrosion or degradation. Nickel alloys are excellent for these purposes. Stainless steel, Inconel, Manel, these are all nickel-based alloys used in aerospace applications precisely because they're robust. A probe constructed from such materials, experiencing heating as it approaches the sun, might release nickel vapor as surfaces ablate or outgas. And if the construction materials were selected to minimize iron content for weight or performance reasons, you'd see exactly what 3I-ATLAS shows. Lots of nickel, not much iron. This explanation doesn't require special chemistry or unusual formation conditions. It just requires that someone built the thing out of materials any competent engineer would choose for an interstellar mission. The fact that the composition matches industrial alloys better than natural materials is, from this perspective, not a coincidence but a clue. Of course, you could flip that argument round. Maybe nickel-rich natural objects exist, and our industrial processes converged on similar compositions because they're functionally optimal. Convergent evolution happens in biology when unrelated species develop similar features in response to similar selection pressures. Maybe it happens in material science too. The cyanide is another piece of the puzzle. 3I-ATLAS produces cyanide, hydrogen cyanide, and carbon-nitrogen radicals at rates comparable to other comets. Cyanide comes from organic compounds in cometary ice, breaking down under ultraviolet radiation and releasing reactive fragments. Nothing unusual there. But the ratio of nickel to cyanide is strange. Typically in comets, metals are trace components while organics dominate. In 3I-ATLAS, nickel emission is nearly as strong as cyanide despite nickel being far less abundant in most cometary materials. The observations suggest either extraordinary nickel enrichment or very inefficient cyanide production, and neither is easy to explain if you're assuming a garden-variety comet. The Keck paper notes this but doesn't dwell on it. They're focused on explaining the nickel, proposing mechanisms for how it could be released and transported through the coma. The cyanide ratio is mentioned almost as an aside, interesting but not central to their analysis. This is typical of scientific papers. They address the question they set out to answer and leave other puzzles for future work. But when you're trying to understand whether 3I-ATLAS is natural or artificial, every anomaly matters. The nickel to cyanide ratio is another data point that doesn't quite fit the standard comet model. There's also temporal variation to consider. Different observations at different times show different nickel intensities. Sometimes the emission is strong, other times weaker. This could indicate that nickel release varies with the rotation of the nucleus, perhaps from localized active areas that point toward the sun periodically. Or it could mean the process releasing nickel is episodic, turning on and off as conditions change. Tracking these variations over time would help constrain the mechanism, but that requires sustained monitoring with instruments capable of detecting nickel emission, and telescope time for that kind of follow-up is hard to secure. Post-perihelion observations in November added another wrinkle. Spectroscopy from multiple observatories confirmed nickel emission persisted even as 3I-ATLAS receded from the sun. The intensity dropped as expected from decreased solar heating, but the nickel didn't disappear entirely. This is consistent with the nickel tetracarbonyl hypothesis. The molecule can form at relatively low temperatures, but it's also consistent with ablation from solid materials as surfaces continue to outgas. Without detailed modelling of both scenarios, it's hard to say which explanation fits better. What would definitively distinguish these hypotheses? Several approaches come to mind. First, high-resolution imaging of the nucleus itself, not just the coma around it. If 3I-ATLAS is made of metal rather than ice, it should reflect light differently. Metals have characteristic polarization signatures. They absorb and re-radiate thermal energy in distinctive ways. Spectroscopy of the nucleus rather than the coma could reveal surface composition directly. These observations are challenging. The nucleus is small and faint compared to the bright coma surrounding it, but not impossible with the best adaptive optics systems or space-based telescopes. Second, measure the nickel isotope ratios. Nickel has 5 stable isotopes with slightly different abundances depending on where the material formed. Supernova ejecta has different ratios than material from planetary cores or the interstellar medium. Industrial refining doesn't change isotope ratios significantly, so artificial materials would show whatever isotopes were in the original ore. If 3I-ATLAS's nickel has isotope ratios matching industrial alloys, that's suggestive. If it has ratios unlike anything from Earth but consistent with a specific astrophysical environment, that tells a different story. These measurements require very high-resolution spectroscopy, probably beyond what's achievable from ground-based telescopes, but may be possible with space instruments. Third, look for other metals that should accompany nickel if it's from natural sources. Cobalt is often found with nickel in meteorites. Chromium and manganese appear in iron-nickel alloys. If 3I-ATLAS shows nickel without any of these companion elements, that's harder to explain naturally than if it shows the whole suite. The Keck data focused on the most prominent emission lines, but careful analysis might reveal fainter lines from other elements that would constrain the composition more tightly. The controversy around the nickel signature illustrates a broader challenge in interpreting ambiguous data. When you see something unusual, something that doesn't match your expectations, there are always two types of explanations available. You can propose natural processes you didn't know about or didn't think would operate in this context. Or you can propose artificial origins. Both approaches can generate hypotheses that fit the observations, at least superficially. Deciding between them requires additional evidence that favours one over the other, and gathering that evidence requires resources and telescope time that might not be available. Scientists generally prefer natural explanations because the prior probability is so much higher. Most things in the universe are natural. The number of artificial objects is vanishingly small compared to natural ones. So when faced with an anomaly, proposing some previously unknown natural process is a safer bet than jumping to alien technology. This is Bayesian reasoning. You update beliefs based on new evidence, but you start from priors that reflect how common different phenomena are. Extraordinary claims require extraordinary evidence precisely because their priors are so low. But priors can be misleading when you're dealing with highly selected samples. Yes, most objects are natural, but 3I-ATLAS isn't most objects. It's an interstellar visitor, something we've only confirmed 3 times in human history. It has multiple anomalies, unusual trajectory, strange composition, unexpected acceleration. The fact that it's already in the extreme tail of the distribution means maybe the priors should be adjusted. If you're trying to estimate the likelihood that a randomly selected object is artificial, using generic cosmic abundances makes sense. But if you're estimating the likelihood that a specific anomalous object is artificial, maybe you should use priors conditioned on it already being anomalous. This is subtle and easy to get wrong. But it matters for how we allocate resources. If you think the prior probability 3I-ATLAS is artificial is 1 in a million based on the fact that most objects are natural, then spending large amounts of money and telescope time investigating that hypothesis seems wasteful. But if you think the prior is more like 1 in 100 based on the specific anomalies this object shows, then intensive investigation becomes justified. Reasonable people can disagree about where in that range the true probability lies, which is why debates about 3I-ATLAS often feel like they're talking past each other. The nickel signature sits at the centre of this debate. To some astronomers, it's an interesting cometary chemistry problem, one more unusual feature of an unusual object, but ultimately explainable through natural processes we're still working to understand. To others, it's a smoking gun, compositional evidence that the object isn't natural at all, but rather constructed from materials chosen for their engineering properties. Both interpretations can point to the same spectrum, the same emission lines, and draw opposite conclusions. What's needed is data that breaks the tie, observations that clearly favour one explanation over the other. December 19th might provide that data, or it might just add more ambiguity to an already ambiguous situation. Either way, the nickel signature ensures 3I-ATLAS will be remembered as one of the strangest interstellar visitors we've encountered, regardless of what it ultimately turns out to be. Institutional Responses and Silence. October 21st, 2025. The International Asteroid Warning Network issues a routine editorial notice. Comet 3I-ATLAS has been added to their monitoring campaign, scheduled to run from November 27th through January 27th. The campaign targets comets that present challenges for accurate astrometric measurements and orbit predictions. Nothing dramatic in the announcement, no mention of alien probes or existential threats. Just dry technical language about exercising the capability of the observing community to extract accurate astrometry. But the fact that IABUN chose to include 3I-ATLAS at all is significant. This is the first time an interstellar object has been added to their threat list, and while the notice carefully avoids suggesting actual danger, the implication is clear. 3I-ATLAS is unpredictable enough to warrant coordinated international monitoring. I-ALAN exists precisely for situations like this, though typically those situations involve asteroids that might impact Earth rather than comets from another star. The network connects observatories and space agencies around the world, facilitating data sharing and coordinated response when potentially hazardous objects are detected. Adding 3I-ATLAS to their campaign means multiple telescopes across multiple countries will be pointed at the objects systematically, measuring positions precisely, tracking any deviations from predicted trajectories, building a comprehensive observational record. This is good. This is how the system should work. And yet there's something unsettling about how quietly it happened. No press releases announced Eon's decision. No, officials explained why an interstellar visitor warranted this level of attention. The editorial notice appeared in the Minor Planet Center's online bulletin system, a resource primarily used by professional astronomers rather than the general public. If you weren't specifically watching for news about 3I-ATLAS, you'd miss it entirely. This pattern of quiet action without public communication characterizes the institutional response to 3I-ATLAS throughout its passage. Things are happening, decisions are being made, resources are being allocated, but the transparency that's supposed to accompany these processes seems to have been suspended. Consider NASA's position. The agency faces multiple pressures simultaneously. There's the scientific question, what is 3I-ATLAS and how do we study it effectively? There's the political pressure, both from Luna's congressional letter and from public interest stoked by the Rogan podcast. There's budgetary constraints, with the government shut down and competing demands for limited resources. And there's the reputational concern. How do we avoid looking either alarmist if we take the artificial hypothesis too seriously, or incompetent if we dismiss it too casually and turn out to be wrong? These pressures don't push in consistent directions. Good science suggests thorough investigation regardless of preconceptions. Political expediency might suggest either dramatic action to show responsiveness, or minimal engagement to avoid controversy depending on which pressure is stronger. Budget realities limit what's actually achievable. Reputation management encourages caution. Don't make claims you can't back up. Don't commit to positions you might have to reverse. The result is often paralysis, doing the minimum necessary to avoid criticism while avoiding bold moves that could backfire. NASA's silence on the high-rise images exemplifies this paralysis. Releasing them immediately would satisfy transparency demands, but might create problems if the images show something ambiguous that gets misinterpreted. Sitting on them indefinitely is clearly untenable given congressional pressure. So what's the middle path? Delay while conducting internal review, claim technical or bureaucratic obstacles, promise eventual release without committing to timelines. It's textbook institutional stonewalling, not because anyone necessarily wants to hide evidence, but because no one wants to be the person who made the wrong call about when and how to release potentially controversial data. ESA faces similar pressures, though perhaps less acute given that European institutions have different political and media environments. The Mars Express and ExoMars observations remain similarly unreleased despite occurring weeks ago. ESA's public statement acknowledged the observations happened and promised results once analysis was complete, but provided no timeline and no preliminary findings. This could be entirely legitimate. Scientific caution, space agencies often wait until peer-reviewed papers are published before making data public. But the timing, coming when interest in 3I-ATLAS is at its peak, makes the wait feel less like normal process and more like strategic delay. The international coordination required for major astronomical observations creates additional complexity. No single institution controls all the relevant assets. NASA has Mars orbiters and Hubble, and Webb. ESA has its own Mars spacecraft and ground-based telescopes. China, the UAE, India, Japan, all have capabilities that could contribute. Getting everyone on the same page about observation strategy and data release policy requires negotiation and consensus building. Different agencies have different protocols, different levels of openness, different thresholds for what constitutes sufficient validation before release. Harmonizing these approaches takes time, and in the meantime, data sits in institutional archives accessible only to researchers with proper credentials. This is where the old model of scientific communication clashes with modern expectations. Traditionally, astronomers observe objects, spend months analysing the data, write papers, submit them for peer review, wait for reviewers and editors to evaluate the work, then finally publish results that become public knowledge. This process takes anywhere from 6 months to several years, depending on the complexity of the analysis and the publication backlog. It's designed to ensure quality, to prevent premature claims that might not hold up under scrutiny. But it's also opaque to outsiders and glacially slow when public interest demands immediate answers. 3I-ATLAS is racing through the solar system on a schedule that doesn't wait for peer review. By the time papers analysing the October observations get published, the object will have passed Earth and be heading toward Jupiter. The December close approach will come and go before any comprehensive peer-reviewed analysis of earlier data appears in print. This mismatch between astronomical timescales and publication timescales creates frustration. People want to know what the Mars images showed now, not in 6 months when a paper finally appears in some journal most people can't access. Social media amplifies this frustration. When Loeb posts on Medium or tweets about NASA's non-responsiveness, his followers share it widely. Thousands of people who wouldn't normally follow obscure disputes about data release policies suddenly have opinions. They demand transparency. They suspect cover-ups. They generate theories about what's being hidden and why. Some of these theories are reasonable extrapolations from available evidence. Others are paranoid fantasies that see malicious intent in every bureaucratic delay. Distinguishing between legitimate concerns and conspiracy thinking becomes difficult when the institutions in question won't communicate clearly about what's actually happening. NASA's social media presence, normally active with beautiful images and exciting mission updates, has been conspicuously quiet about 3I-ATLAS. A few generic posts acknowledging the object's existence and reiterating that it poses no threat to Earth, but nothing substantive about the science or the observations. This might reflect simple prioritization. The agency has many missions and many stories to tell, and 3I-ATLAS isn't necessarily the most important. But it might also reflect an institutional decision to minimize public engagement on a topic that's become politically fraught. Don't say much, and you can't be accused of saying the wrong thing. The contrast with how NASA handled previous interstellar visitors is striking. When Oumuamua was discovered, the agency issued press releases, gave interviews, published beautiful graphics showing the object's trajectory. Scientists from NASA facilities appeared in documentaries and news segments explaining what made Oumuamua special. There was celebration, excitement about observing humanity's first confirmed interstellar visitor. The fact that Loeb later proposed an artificial origin hypothesis generated some controversy, but the initial response was enthusiastically public. 3I-ATLAS has received much more muted treatment despite being larger, brighter, and more extensively observable than Oumuamua ever was. Why? Perhaps because the artificial origin hypothesis emerged earlier this time, before the initial burst of enthusiasm could establish a comfortable natural explanation as consensus. Perhaps because the political environment has changed, with more public skepticism about government institutions and more willingness to believe in conspiracy theories. Perhaps because NASA learned from Oumuamua that interstellar objects generate intense speculation that's hard to manage, and decided to keep the communication channels tighter this time. Whatever the reason, the effect is to make NASA look defensive and secretive, even if that's not the intent. Silence gets interpreted as having something to hide. Delays get interpreted as cover-up. Generic reassurances that the object poses no threat get interpreted as dismissive arrogance. How can they be so sure if they won't share the data showing why they're sure? This is a losing communication strategy, but it's also a very human one. When you're unsure what to say that won't make things worse, sometimes you say nothing. Sean Duffy, NASA's acting administrator, has his own complications. He's simultaneously serving as transportation secretary and overseeing NASA during a transition period. His attention is split between multiple massive bureaucracies with very different mandates. He's dealing with the SpaceX moon contract controversy, questioning whether Starship is on schedule and whether NASA should open up competition to other providers. He's managing the fallout from the government shutdown and trying to restore normal operations. 3I-ATLAS, whatever its significance scientifically, is probably not his top priority compared to multi-billion-dollar contracts and Chinese competition in space. That doesn't excuse the lack of response to Luna's letter. When a member of Congress formally requests information, the executive branch is supposed to respond. Maybe not immediately, maybe not with everything requested, but at least with acknowledgement and explanation. As of early November, no such response has appeared publicly. Luna's office hasn't announced receiving a reply. NASA hasn't issued a statement addressing her 6 specific requests. This silence is becoming its own story, evidence of institutional dysfunction regardless of whether there's any deeper issue with the data itself. Representative Luna's intervention represents an interesting case study in how politicians can influence scientific institutions when they choose to engage. Luna isn't on any of the committees that normally oversee NASA. She's not a scientist herself, but she's a member of Congress, which means she has access to institutional leaders and the ability to make requests that carry weight beyond what any individual scientist can achieve. Her willingness to stick her neck out on this issue, to formally request data about an object that most of her colleagues probably haven't heard of, suggests either genuine interest in the scientific question or recognition that her constituents care about it. Either way, it's unusual. Most congressional oversight of space agencies focuses on budgets, contracts, and workforce issues. Science policy gets discussed in general terms: should we go to Mars, should we fund a space telescope, that kind of thing. Rarely do individual legislators get involved in specific observational programs or data release decisions. Luna's letter changes that dynamic, bringing political pressure to bear on what would normally be purely scientific and bureaucratic processes. Whether this is helpful or harmful depends on your perspective. Scientists might resent political interference in their domain, but if that interference forces transparency that wouldn't otherwise happen, maybe it serves the public interest. There's also the question of what other governments know and aren't saying. The Chinese National Space Administration has assets in Mars orbit. The UAE's HOPE mission is there. If their instruments observed 3I-ATLAS during the October approach, do they have data NASA doesn't? And if so, are they sharing it through the usual scientific channels or keeping it for their own analysis? International space cooperation works reasonably well in normal circumstances, but when something unusual or potentially significant is involved, national interest can override scientific openness. Imagine if China's Tianwen-1 orbiter captured images showing clear structure in 3I-ATLAS that couldn't be explained as natural. Would they immediately release that data to the international community, knowing it would generate massive attention and speculation? Or would they analyze it internally first, verify the findings, consider the implications, and only then decide how to proceed? And what if the images are ambiguous, showing something interesting but not definitive? The calculus becomes even more complex. Release ambiguous data and get criticized for creating confusion. Sit on it and get accused of cover-up if it eventually leaks. There's no obviously correct choice. This brings us back to the fundamental tension between scientific ideals and institutional realities. Science is supposed to be open, with data and methods shared freely, so anyone can verify and build on previous work. But science is done by institutions that have legal obligations, political pressures, competitive dynamics, and public relations concerns. These factors don't necessarily align with the ideal of immediate total transparency. Sometimes they actively conflict with it. The Arwen campaign represents one version of institutional response that actually works reasonably well. Multiple observatories coordinating to gather comprehensive data without drama or controversy. Results will be shared through standard scientific channels, papers will be published, and the community will evaluate the findings collectively. This is the system functioning as designed. It's just not fast enough or transparent enough for an age where people expect real-time updates on everything. What would optimal institutional response to 3I-ATLAS look like? Probably something like this. Immediate release of all observational data to public archives, even raw uncalibrated data, so anyone with expertise can analyze it. Regular press briefings updating the public on findings and remaining questions, acknowledging uncertainties rather than pretending to certainty before analysis is complete. Active engagement with scientists proposing unconventional hypotheses, testing those hypotheses rigorously rather than dismissing them. Allocation of significant resources to intensive observation campaigns during key windows like the December close approach. And clear communication about timelines when we'll know more, what observations are planned, what they might reveal. We're getting some of this, but not all of it. The IAWN campaign is a step in the right direction. Individual scientists like Loeb are engaging publicly, even if institutions won't. Amateur astronomers are filling gaps in the observational record. But the overall response feels disorganized, reactive rather than proactive, more concerned with avoiding controversy than with maximizing scientific return. And the silence from NASA on the basic question of why the high-rise images remain unreleased continues to undermine trust in the process. Maybe December will change things. Maybe when 3I-ATLAS reaches closest approach and major observatories turn their instruments toward it systematically, the accumulated data will be so rich and unambiguous that everyone agrees on the interpretation. Maybe that interpretation will clearly favour natural origins and put the artificial hypothesis to rest. Or maybe it will reveal something genuinely anomalous that forces institutions to take the possibility seriously. Or maybe, most likely, it will be ambiguous enough that debates continue, but at least there will be more data to debate about. The institutional silence can't last forever. Eventually someone will have to say something substantive. We're just waiting to see who breaks first and what they say when they do. What December will reveal, December 19th, 2025. Mark that date. 1.8 astronomical units, roughly 270 million kilometres, the distance that will separate 3I-ATLAS from Earth at closest approach. Not particularly close by cosmic standards. The Moon is 400 times nearer, but close enough. Close enough that the best telescopes on Earth can resolve features down to 10 or 15 kilometres across. Close enough that spectroscopy can measure composition in detail. Close enough that radar might work if anyone attempts it. Close enough that if 3I-ATLAS is hiding secrets, we'll have our best chance to discover them. The geometry matters. Throughout most of its passage through the inner solar system, 3I-ATLAS has been viewed from difficult angles or at distances that limit resolution. The early observations when it was discovered in July showed a faint moving dot. Hubble's images from late July and August revealed a coma and hints of structure, but from a nearly edge-on perspective. The October Mars observations, still unreleased, came from a sideways angle, but at 30 million kilometres. December offers something better. A relatively close approach with 3I-ATLAS positioned away from the sun's glare, observable through long nights for Northern Hemisphere observers, positioned where Earth's atmosphere is reasonably transparent. Every major observatory is making plans, assuming they haven't already committed their schedules to other programs. Hubble will almost certainly observe. It's the premier visible light-space telescope, and 3I-ATLAS is exactly the kind of target it was designed to study. The Webb telescope, with its infrared capabilities, can detect thermal emission from the nucleus and measure how heat is distributed across its surface. Ground-based telescopes with adaptive optics, systems like the Keck telescopes in Hawaii or the Very Large Telescope in Chile, can achieve resolution competitive with space telescopes for bright objects. Radio telescopes might attempt to detect signals or use radar to probe internal structure. Amateur astronomers are planning too. The object should be faintly visible in moderate-sized telescopes, bright enough that experienced observers with good equipment can capture images and spectra. This democratization of astronomy means the professional observations will be supplemented by thousands of amateur data points. Some will be low quality, but some will be excellent, catching things that professionals miss simply because no one can point every telescope at every patch of sky simultaneously. The distributed network of observers ensures that if 3I-ATLAS does something unusual, if it suddenly brightens or changes appearance or ejects material, someone will probably notice. What specific questions can December observations answer? Start with the most basic: size. We have estimates of 3I-ATLAS's diameter ranging from less than a kilometre to over 5 kilometres, depending on assumptions about albedo and composition. High-resolution imaging can measure the actual size directly, seeing the physical extent of the nucleus rather than inferring it from brightness. This matters because size determines mass if you know density, and mass determines how much force is needed to produce the observed acceleration. If the nucleus is smaller than 5 kilometres, the natural explanation for non-gravitational acceleration becomes harder. If it's larger, natural explanations work better. Shape is another question. Is 3I-ATLAS roughly spherical like you'd expect from a body held together by its own gravity? Or is it elongated, maybe even dramatically elongated like Oumuamua appeared to be? Shape constrains formation history and structural strength. Natural comets tend towards spheroidal shapes unless they're small enough that tensile strength can support non-spherical geometries. Artificial objects can be any shape engineering requires. An extremely elongated object, especially one with straight edges or planar surfaces, would be very hard to explain naturally. Surface features matter too. Does the nucleus show craters from impacts during its journey through space? Are there jets or active regions where outgassing is concentrated? Are there colour variations suggesting different compositions in different areas? These details tell stories about the object's history. Pristine surfaces without craters might indicate the object is young, or spent most of its existence in regions of space where impacts are rare. Heavily cratered surfaces suggest age and exposure. Active regions reveal internal structure, where volatiles are concentrated, how heat propagates through the interior. The coma deserves intensive study. Is it symmetric or asymmetric? How does the brightness distribution change with distance from the nucleus? What's the mass loss rate? And how does it compare to the rate needed to explain the trajectory anomalies? The critical test Loeb keeps emphasizing is whether we see evidence of the 5 billion tons of material that should have been ejected if non-gravitational acceleration came from outgassing. That much material makes a visible cloud. If the cloud is too small, the natural explanation fails and we need an alternative. Spectroscopy can measure dozens of molecular species in the coma. Water, carbon monoxide, carbon dioxide, cyanide, these are expected. But look for unusual abundances or unexpected molecules that might hint at non-natural processes. The nickel-to-iron ratio remains important. Other metals, rare volatiles, anything that doesn't fit the standard cometry composition deserves attention. Anisotope ratios if they can be measured precisely enough. These are fingerprints of origin, ways to distinguish between materials formed in our solar system, other stellar systems, or potentially in industrial processes. Then there's the question of multiplicity. Is 3I-ATLAS one object or several? The mini-probe hypothesis predicts that careful imaging might reveal smaller objects travelling near the main nucleus. These wouldn't be fragments from a breakup. Fragments disperse chaotically. They'd be separate objects on controlled trajectories, maintaining formation flying in ways that natural fragmentation doesn't produce. Detecting this requires exquisite position measurements and probably multiple epochs of observation to see how the relative positions change over time. Rotation provides another diagnostic. All comets rotate, and rotation period tells you about internal structure and formation history. If 3I-ATLAS rotates very slowly, that might indicate it's larger or denser than expected. If it rotates rapidly, it needs tensile strength to avoid flying apart under centrifugal forces. Changes in rotation period, either spin up or spin down, would suggest mass redistribution or torque from jets. Measuring rotation requires tracking brightness variations or surface features over hours or days, a campaign that needs consistent telescope access. Polarization measurements, while technical and unglamorous, can reveal surface properties. Different materials polarize reflected light differently. Ice, rock, and metal all have characteristic polarization signatures. The extreme negative polarization measured earlier in 3I-ATLAS's passage was anomalous. Confirming it with higher quality data would be important. If the polarization normalizes at close approach, that tells one story. If it remains extreme, that tells another. Thermal observations with infrared telescopes can measure surface temperature and how it varies across the nucleus. Temperature distribution depends on thermal inertia, how quickly different materials heat and cool. Rocky surfaces behave differently than icy ones. Metallic surfaces are different still. Mapping temperature at high resolution could reveal whether 3I-ATLAS is the fluffy ice ball most comets are, or something with higher thermal conductivity. And of course there's radar. This is speculative because radar observations of small distant objects are challenging and require high-power transmitters. But if attempted, radar can probe beneath the surface, measuring internal structure, detecting voids or layers or variations in composition that aren't visible optically. Radar can also measure very precise distances and velocities, potentially detecting the tiny accelerations that might indicate propulsion. Whether anyone with access to planetary radar systems attempts this depends on convincing them it's worth the effort. All of these observations generate data, and data needs analysis. Images need to be processed, spectra need to be calibrated, measurements need error analysis. This takes time, realistically weeks to months before definitive results appear in publications. but preliminary findings should emerge quickly, probably within days of the observations. Scientists will post preprints, write blog posts, give conference talks, share results through informal channels long before formal papers appear. The December observations will generate a burst of information, some reliable, some tentative, some wrong but corrected quickly as more data comes in. The International Asteroid Warning Network campaign provides a framework for coordinating observations and sharing data. Their mandate is astrometry, precise position measurements to refine the orbit, but the campaign creates infrastructure that can support other observations too. When multiple observatories are already pointed at 3I-ATLAS for position measurements, adding spectroscopy or imaging or other techniques is relatively straightforward. The campaign runs through late January, providing sustained attention through the critical post-perihelion period. But let's be realistic about what December probably won't resolve. Unless 3I-ATLAS does something dramatic, something that unambiguously indicates artificial origins like transmitting radio signals, or visibly manoeuvring, we're likely to remain in the realm of ambiguity. Most measurements will have error bars. Most observations will be consistent with multiple interpretations. The natural versus artificial debate won't be settled by a single smoking gun observation, but rather by the accumulation of many observations that collectively favour one explanation over others. And even then, consensus takes time. Scientists will disagree about what the data means. Some will see evidence of unusual but natural processes. Others will see hints of artificial origins. Debates will play out in papers and conference presentations and blog posts. The media will cover it, probably sensationalizing the controversy and making it sound more polarized than it actually is. Social media will amplify extreme positions while moderate views get less traction. This is normal. This is how science works on questions where evidence is genuinely ambiguous. The tragedy would be if December observations don't happen at all or happen inadequately. If budget constraints or scheduling conflicts or institutional inertia means the best telescopes aren't pointed at 3I-ATLAS during closest approach. If data gets collected but sits in archives unanalyzed because no one has time or funding to do the work, if observations happen but results don't get shared openly because of publication embargoes or intellectual property concerns, these would be failures of the scientific system, lost opportunities that we can't get back because 3I-ATLAS won't return. There's also the human element. Astronomers are excited about 3I-ATLAS. It's genuinely interesting regardless of what it turns out to be. But excitement doesn't always translate to action when there are obstacles. Telescope time is competitive. Analysis requires funding. Publishing requires navigating peer review. Career advancement requires choosing research that advances your reputation. Risky investigations of controversial objects can backfire if they don't pan out. These pressures shape what research gets done and what doesn't. Loeb's advantage is that he's already established enough that he can take risks others can't. But even he needs collaborators, telescope access, funding for students and postdocs to do the detailed analysis. The Galileo project provides some of that infrastructure, but it's limited compared to what NASA or ESA can marshal when they commit to something. If 3I-ATLAS were recognized as a high-priority target by the major space agencies, resources would flow. Dedicated observation campaigns would be organized, the best instruments would be allocated. That recognition hasn't happened yet, at least not publicly. December 19th is one day, but the observation window extends weeks on either side. 3I-ATLAS will be well positioned for observation throughout late December and into January as it continues outbound. The Iron campaign extends through late January, maintaining coordinated monitoring. So even if weather or technical problems interfere with observations on the date of closest approach, there are other opportunities. But closer is better. Resolution degrades with distance. Every day after December 19th makes the observation slightly harder. Think about what we're hoping to learn. At minimum, precise characterization of an unusual interstellar object that will refine our understanding of what materials and structures can form in other stellar systems. That's valuable science regardless of origin. At maximum, confirmation that humanity is not alone, that intelligent civilizations exist elsewhere and have technology capable of interstellar travel. That would be transformative, the biggest discovery in history changing our understanding of our place in the cosmos. The probability of the maximum outcome is low, but non-zero. The expected value, probability times impact, is enormous. That's the calculation that should drive observation strategy. Even if you think there's only a 1% chance 3I-ATLAS is artificial, the potential payoff is so large that treating it seriously makes sense. This is Pascal's wager applied to astronomy. The cost of investigating thoroughly and being wrong is manageable, some telescope time, some careers, some embarrassment. The cost of not investigating and missing evidence of extraterrestrial intelligence is catastrophic. We'd have failed to recognise the most important discovery possible because we were too conservative or too proud to look carefully. December will reveal some things. It won't reveal everything. But it represents our best shot at understanding what 3I-ATLAS is before it passes beyond reach of our instruments. What happens depends partly on whether observations are planned and executed well, partly on whether 3I-ATLAS cooperates by being observable when we look, and partly on luck. Good weather, functional instruments, skilled observers making the right choices about what to measure and when. All of these factors matter. And then there's the question of what comes next. 3I-ATLAS will continue toward Jupiter, reaching closest approach in mid-March 2026. The Juno spacecraft will be there, potentially able to observe from close range if NASA extends its mission and directs it appropriately. That's the request Luna made in her letter. Whether Juno gets that mission extension depends on budgets and priorities, and whether NASA decides 3I-ATLAS is worth the effort. If December observations reveal something truly anomalous, the case for Juno observations becomes stronger. If December is ambiguous, the political will to extend Juno might not materialize. After Jupiter, 3I-ATLAS exits the solar system, accelerating as the sun's gravity slingshots it back into interstellar space. Within a few years, it will be too distant for even our best telescopes to detect. The window for study is finite, measured in months, not years. What we learn now, or not at all. That urgency should focus attention, should drive institutions to act decisively, should overcome the inertia and caution that normally slows scientific response. Whether it actually does depends on factors beyond scientific merit, on political will and public interest, and the individual decisions of people in positions to allocate resources. So December 19th stands as a marker, a moment when ambiguity might resolve or deepen, when questions might be answered or multiply. It's not an ending. 3I-ATLAS's story will continue into 2026 and beyond as analysis of December data proceeds, and as later observations from Juno or other assets add information. But it's an inflection point, a time when the trajectory of our understanding could shift significantly depending on what the data reveals. We wait, we prepare, we hope that the observations happen as they should, and that whatever truth 3I-ATLAS carries becomes visible to those willing to look.